Hello, everyone. Welcome to the October 2022 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. Delayed a little bit this month. Usually we try to go for the first Monday of the month with the AMAs, but we wanted to hit last week with TMA Aganabuzz podcast, the beginning of World Space Week, since we were talking about space, and Timmy is one of the former, I guess, directors of World Space Week or something like that. So anyway, here we are with the AMA. Many things going on. Just had a book come out. You may have heard The Biggest Ideas in the Universe, Space, Time, and Motion, Volume 1 of the 3-volume trilogy. The book launch has gone well. I'm teaching courses at Johns Hopkins and so forth, so there's a lot going on. I don't want to waste too much time with a long introduction here. Just wanted to say huge thanks to everyone who has been donating to the Mindscape Big Picture Scholarship Fund. This is a scholarship fund at bold.org that people can apply for if they're in high school or university and will be still attending university in the future and going to be studying to become someone who studies the big ideas, whether it's physics or philosophy or math or biology, neuroscience, whatever, but the fundamental nature of reality in a deep way. If that's the kind of thing that you want to study in college, you could apply for the Mindscape Big Picture Scholarship. If not, you can always donate money to the Mindscape Big Picture Scholarship. Go to bold.org/scholarships/Mindscape. And the very good news is we're giving away scholarships that will be $10,000 each. We have enough to fund 2 scholarships, and we're actually very close to having enough to fund 3 scholarships, which is amazing. Huge thanks to everyone who's contributed. You're really, I think, trying to make someone else's life better in a really interesting and different way. For those of you who are new around here, these Ask Me Anything episodes are funded by Patreons, or patrons, I suppose, of the Mindscape podcast, people who contribute on Patreon. If you go to patreon.com/Sean M. Carroll, you can both get ad-free versions of the podcast and also ask the questions that I will go about answering right now. So let's go. I should start by saying that, of course, we have too many questions. As usual, I try to pick ones I think I can give interesting answers to. There are things called priority questions. Once in your life, you're allowed to ask a question that I promise I will do my best to answer. But also, apparently this month, again, this happens sometimes, but Patreon cuts off some people's typing or something like that. It seemed that there were a few questions that began but didn't end. So I'm not answering them, but just make sure to check once your question is submitted whether or not it's actually showing up before you go about trying to answer them. So to begin then, Ken Wolf says, I've been reading The Weirdest People in the World by Joseph Henrich, former Mindscape guest. One point he makes early on is how profoundly the spread of general literacy has changed the way people think. Just one example is how it makes us lean heavily toward reductionist rather than holistic thinking. Do you think that the spread of literacy has been something close to an unalloyed good, or do you think that something important might be disappearing from the human condition as we all move in that direction? I would say this is a very good question. Of course, I'm not an expert in this, so this is just, me giving my incredibly untutored personal take. But I think that it's not an unalloyed good necessarily, because most goods are not unalloyed. But I think that literacy is an overwhelming good. Maybe there are some disadvantages. Maybe it has made us lean toward being reductionist. But man, it's worth it. Literacy is one of the most important things in the world. So, how do you balance these things? How in the world do you even answer the question, is it worth it overall, if you have some disadvantages and some advantages? But I think that for literacy, the ability to read, as someone who is literally reading this question right now, and someone who writes books, someone who writes articles, all of these things, of course, I'm going to say that literacy is overwhelmingly advantageous. If you don't want to be literate, you don't have to learn, I guess, or you can forget. You can just stop reading. That's okay, but I don't think many people are going to be doing that. Jimmy says, imagine you build a computer that tells you whether a number is prime, outputting a 1 if it's prime and a 0 if it's not. Imagine then that you put in the number 13 and receive an output of 1. You can then ask the question, why were those particles that represent an output of 1 in that particular place at that particular time? You could answer it by telling a story from the Big Bang, blah, 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 or you could say that it was a mechanism designed to determine primes. The number 13 was input, so they represented an output of 1. Both explanations seem valid, but are they equal? The sort of reductionist, going back to the Big Bang one, versus the higher level, trying to get a prime number one. My intuition says that the latter explanation is not just more useful, but in some way actually more accurate. What do you think? So I don't think that I quite agree with your intuition, but I get your intuition. I think that there are two ways of talking about it. I wrote a whole book, The Big Picture, that talks about poetic naturalism and the multiple levels at which we can think about the world, all of which can be thought of as valid. So I don't think it makes much sense, or at least I don't see the argument for saying that the higher level explanation, that you say that the reason why these things happen in a certain way is because the number 13 is prime, is more valid. It might be more explanatory. You might imagine that there is some sense in which we can rank the explanatoriness of different explanations by some version of how much you get out versus how much you put in, right? For the explanation in terms of the Big Bang and the physics of elementary particles and so forth, you really actually have to put in a tremendous amount of information before you get out the prediction that the computer will say 1 because 13 is prime. Whereas if you just think about abstract symbol manipulations and the number 13, you don't need much input to say, yes, this number is going to be prime. But that doesn't make it more valid. More valid, validity is just, is it true or is it false, right? Or does it work or does it not? That is not a measure of efficiency. I think maybe what you're looking for is efficiency or something like that. And yeah, I absolutely think that levels of explanation might have varying degrees of efficiency. And absolutely, it makes more sense if you're a computer programmer to think of this level of prime numbers, not at the level of elementary particles and the Big Bang. Elliot Specht says, the Webb telescope has recently been used to detect CO2 in the atmosphere of an exoplanet. To use this result to calculate the probability of finding life there, we need the prior probability. We can use other data to estimate the prior, but Bayes' theorem applies all the way down, so any inference from observation ultimately depends on a credence developed with no data whatsoever. So how can I defend as rational conclusions which depend on data-free credences? Well, I think there's two things. One is a small footnote. It's not that the credence is developed with no data whatsoever. The credences that we develop as priors have something to do with who we are in some very broad sense. Our biology, our psychology, our neuroscience, our education, our upbringing, our intuitions, the evolutionary history that brought us here. We are embodied creatures living in the world, and that all counts as data in some sense, right? We have experience with the world. We have a way of thinking about things, and these ways of thinking about things that seem natural and intuitive to us feed into our priors. They're not completely arbitrary priors. But that's a footnote. I think there's nevertheless a point here, which is that there's just the primary worry about Bayesian reasoning is that people start with different priors. That's true. And you're not going to get around that because people do start with different priors. There's just no choice, right? I mean, that's just how reasoning works. If you want to say, what is the chance that some theory I don't know is whether it's true or not, what is the chance that it's true? Different people are going to have different ideas. That's not a bug. That's just a feature. The rationality comes in when you reason from the beginning point of having that prior. Having priors that are weird to the rest of us might be unreasonable, but are not irrational, if you know what I mean. The rationality has to do with the process that you use to make logical deductions from those starting points. And Bayesian reasoning is just a tool that you use when you're dealing in situations of uncertainty. There's really no choice about it. So you can talk to other people about their priors, and you can sort of hand wave yourself into arguing in favor of a prior, right? You can say, well, chemistry, I've learned certain things, laws of physics, it's a big universe, whatever it is. And people may or may not agree with you. But if you collect enough data, the word enough is going to be doing a lot of work here, but if you collect enough data, good Bayesians will always converge on the same answers. So that's ultimately going to be the true way to be rational about these things. Chris Murray says, in one of the biggest ideas in the universe videos, you mentioned that one of the things the Hamiltonian formulation of classical mechanics does is allow P equals mv, momentum equals mass times velocity, to be not the definition of momentum, but a physical law we might violate. Is there value in considering physical quantities other than momentum in the same light? Well, maybe. I'm answering this question not because I have any brilliant insight on it, but it's a cool question. So I think it's an insightful question. Do we know that certain things that we define aren't actually better thought of as dependent variables that we should think of as solving some equations rather than just being defined to have the values that they do? I don't think that physicists usually think that way. Maybe they should. Maybe that would be a useful way to think. But physicists very often will take something they think is a constant and say, well, what if it's a variable? Like that happens all the time. What if Newton's constant of gravity is a variable, right? That's what Bronsted-Dickey did a while back to invent Bronsted-Dickey theory of gravity and so forth. There's more examples like that. In the particular case of momentum equals mass times velocity, it is an implication of Hamiltonian mechanics, but the fact that that equation is an equation of motion rather than a definition is an implication of Hamiltonian mechanics. But I don't think that's the motivation that led Hamilton to invent Hamiltonian mechanics. I'm not exactly sure what his motivation was, but I think that's a result that popped out. So the other reason I want to answer this question is just to sort of highlight the difference between something turning out to be true that we hit upon by some line of reasoning and using that kind of thing as a starting point, right? A motivation. So it worked for momentum, turning it from a definition into a free variable that we could then solve as an equation of motion, but maybe or maybe not, it will work any other way. So I'm happy to let people try, but I don't think that we should get the impression necessarily that that is a surefire way to get better laws of physics. Nalita S. says, the many worlds interpretation of quantum mechanics is mind-boggling, and it kind of makes one wonder about a mysterious phenomenon that some lucky ones experience often, like seeing in one's head an event or person as an image, only to be followed by the manifestation of that thought in real life. How would you as a physicist and philosopher interpret those mysterious events? Well, I personally would interpret them as having nothing to do with quantum mechanics. I think that the brain and how the brain works is way more complicated and way harder to understand than quantum mechanics is. There's enough going on in the brain that we know that, number one, we make mistakes all the time. We hallucinate things, we misperceive things. You know, when linguists study how we comprehend language, whether it's listened to or read on a piece of paper, our brain is constantly filling things in. We're not hearing every sound or reading every letter. Likewise, optical illusions are a great example of where we see things and our brain forces them into a certain kind of pattern, even though the pattern might not be the right one. That's why it turns out to be an illusion. Furthermore, retrospectively, we often give greater weight to things that we think are surprising and cool and interesting and provocative, rather than objectively collecting data in some numbers of times that something happens versus how many times you'd expect it to happen, like a good Bayesian. So given that, I think there's plenty of reasons based on the laws of physics to think that quantum mechanics has nothing to do with seeing things either that haven't happened yet or that are happening far away. I think that I would blame the tricks of the brain for that rather than the rules of quantum mechanics. Kavadin says, could you help me understand irrational numbers? Specifically, why do mathematicians give importance to certain irrational numbers like I and pi, but not others like x divided by 0? Or does the fact that the number is irrational tell us more than the number itself? Why are these numbers so important in physics? So I think that we've missed the definition of irrational number here. So irrational numbers to mathematicians or to physicists don't just mean weird numbers or special numbers. That means specifically real numbers, so not imaginary ones like I, the square root of -1, and actual numbers, not like x over 0, which is not even a number, but real numbers like pi or like the square root of 2, but numbers that cannot be expressed as a fraction of two integers, right? Pi is very, very close to 22/7, but 22/7 is the ratio of two integers, and pi is not the ratio of any two integers. That's what makes it an irrational number. Irrational numbers are very, very important. If you have some span of real numbers, like all the real numbers between 1 and 2, almost all of them are irrational. There are far, far more irrational numbers than rational ones. So why are they important in physics and math? Just because they're a crucial part of making up the continuum of the real line, not to mention the real plane or the real other things. Anytime you have a continuum, irrational numbers are a big part of the game. Nicholas Sharowski says, I've heard you say several times that you're glad to be doing physics because it's much easier than other sciences. However, I sometimes feel that natural scientists look down a bit on other social sciences like psychology, sociology, linguistics, etc., because they have different methodological foundations. How would you respond to someone who says sociology is not a real or genuine science? Well, I think that they're very different activities, sociology and physics, but I definitely think that they're both science. I mean, to me, science is the attempt to explain the world by developing models and testing them against data, right? That's what science is. And that those models can be about society or people or language just as much about chemistry or physics or whatever. So someone who says sociology is not a real science is just not paying attention or just trying to start a fight or whatever. I'm not going to spend a lot of time arguing with them. Now, the reason why I say physics is much easier than other sciences is somewhat tongue-in-cheek, of course. Actually becoming a physicist is not necessarily easier than becoming any other kind of scientist. I would say that becoming a really, really good physicist is about equal difficulty to becoming a really, really good linguist or psychologist or whatever. But that's because human beings have certain capacities, and in any one of those fields, you sort of push your capacities to the utmost and see how far you can get. What's easier in physics really is not just becoming a professional physicist, but making progress. That's the real thing that characterizes physics. It's way easier to make progress because physics very often deals with very simple systems, a pendulum rocking back and forth, an electron field vibrating, whatever it is. Very, very simple compared to society or the human brain or the structure of language and so forth. So that's why physics seems hard, because we can learn a lot about it because we're able to make progress by studying simple systems, which is not possible elsewhere. And for someone just to say that something that does aspire to thinking about and hypothesizing and saying true things about very, very complicated systems like psychology or sociology, etc., is just not paying attention, I think. Now, having said that, of course, it's always possible to say that a certain field of endeavor is, on average, not doing nearly as well as it could at its own aspirations, right? You could say that there are just methodological flaws in psychology or sociology, just like you can say there are methodological flaws in physics. But if you want to say that, you got to say exactly what those flaws are, and you got to back it up by actually having some evidence in favor of that claim. I'm going to group together two questions here because they're the same question and then they just came out of somewhere. Sugar Pine Press says, could you please spend a little time unpacking the fine structure constant? Is it significant that it has no units? Does a theoretical multiverse and anthropic argument truly reduce it to, no big deal? Does it play any role in your thinking about what space-time emerges from? And then Nick G says, is there something unique or special that differentiates the fine structure constant from the coupling constants of other forces? Seems like there's one unique constant for each force, yet the fine structure constant gets all the hype. So the fine structure constant is being implied here, part of a list of constants of nature that we have in, let's say, the standard model of particle physics. All the constants of nature, I guess not all of them, but it's weird how different they all are in some sense. The fine structure constant is interesting because it is dimensionless, so it's a number, which means that it doesn't depend on what units you use to measure it. Everyone should agree that the fine structure constant, once you tell me its definition, has the value approximately 1 over 137, whereas Newton's constant of gravity, depending on what units you use, will have different forms, different numerical values. It is not the only constant in the standard model of particle physics that is dimensionless, but the others, have different sort of statuses. So like for the weak interactions, you know that the weak interactions are unified with the electromagnetic interactions, and there's two more numbers that come in there. One is the expectation value of the Higgs field, and that is a dimensionful quantity, and that's a puzzle. We don't understand why it has the value it does. The other is what's called the weak mixing angle, or the Weinberg angle, and that is dimensionless, but it's an angle, which means that it can only possibly take on values between, let's say, 0 and pi. because it wraps around and it's sort of equal to itself if it goes past pi. So it's a little bit different than just a number like the fine structure constant. An angle has a constraint that the fine structure constant doesn't. But I do think that to actually get at the question, there is a lot of historical analysis going on here. We figured out electromagnetism, and in particular, we figured out quantum electromagnetism before we figured out any of the quantum theories of the other fundamental forces. So it popped out that we had this dimensionless number in QED, quantum electrodynamics, before we knew really what to say about the other ones. I should also mention the strong interactions, which in some sense also have a dimensionless number associated with them. But it's harder to tell you what that number is because in quantum field theory, numbers that are coupling constants depend on the scale at which you measure them. And for the fine structure constant of electromagnetism, you can just take the limit as you're measuring it at zero energy and define that to be the number. At higher energies, the number would change a little bit according to the renormalization group. But with the strong interactions, the number seems to blow up at zero energy. So what you do instead is say, what is the energy scale at which the strong interaction coupling constant becomes of order 1? And that is called the QCD scale and is a dimension-full number. It is around a third of a GeV, a third of the mass of the proton. So even though in some way of thinking classically at the level of the Lagrangian, if you want to put it that way, the strong coupling constant is dimensionless, you really need a dimension-full number to specify what it is. So it's really the fine structure constant that is the most obviously dimensionless of any of the fundamental structure constants. I don't think that it means that it has any fundamental role in quantum gravity or anything like that. It's about electromagnetism. I think that's the right way to think about it. Okay, Nichol, I'm sorry. It says here Nichol, as if it were Michael, but with an N. So I'm going to assume that is just correct. And this is Nichol Kramer says, despite reading all the popular accounts of the Higgs field that I can find, I'm afraid I still don't quite understand how it adds mass to the affected particles. Most of these accounts describe the field and how it interacts with the affected particles, but then it seems that, presto, the particle has mass. Can you help me out here? Well, I don't know if I can help you out or not. I'm the author of one of those popular accounts of the Higgs field, so I do my best. But the problem is that I'm not sure what it is about those accounts that is leaving you cold or leaving you unsatisfied. So I'm not sure that I'll be able to patch up that particular hole. But here's a way of thinking about it that might be a little bit different than what we normally think. You know, what is mass after all? So basically, I think the right way to think about mass is what Einstein taught us, that E equals mc squared. Mass is a kind of energy. It's the energy an object has when it's just sitting there not doing anything, right? No kinetic energy, no potential energy. It just has existence energy, and that energy is this mass times the speed of light squared. Or rather, what we call the mass is that rest energy divided by the speed of light squared. So where does it come from? Why does a particle in fundamental physics have energy when it's just sitting there? Well, if particles are massless, I guess the right thing to say is this. In modern physics, all of these particles come from fields. It's not just the Higgs boson that is a field. The electron is a field. The quarks are fields. All of these things are fields, and they're vibrating fields. And the vibrations have different kinds of energy associated with them. There's kinetic energy, which means the field's time derivative gives you a kind of energy. How fast is it vibrating? There's gradient energy. How is the field changing from place to place? That's a kind of energy. And there's also potential energy. And the potential energy is not how the field is changing from place to place, but just what is the energy associated with the value of the field. So you might think in your mind that if the field has zero value, it has zero energy. And if it has a non-zero value, maybe it does have an energy. Okay. That's not always exactly right. In fact, famously for the Higgs boson, that's not true. The energy is not zero at zero field value. That's why the Higgs field takes on a non-zero value in empty space. The lowest energy state is not at zero field value. But this is that story is true for all of the fields. So the photon is massless and it doesn't have any potential energy. At the field level, the mass of a field comes from its potential energy. And this is not going to be very satisfying maybe, but you can kind of see that connection. Einstein says the mass of an object is the energy it has just sitting there. Quantum field theory says the mass of a field is the energy you get just from having a value, not necessarily from changing. But for something like the photon, there's no potential energy. There's no energy associated with the field having a value. In fact, the value of the field, this is the something that is wrapped up in what we call gauge invariance or gauge symmetry. The value of the field doesn't matter, only how the field changes from place to place. And indeed, when you get into the math, only certain aspects of how it changes from place to place is what really matters. So the field for electromagnetism is not the electric field or the magnetic field. It is what we call the vector potential field, which gives rise to the electric field and the magnetic field, depending on how it's changing over space or over time. So because there is no actual energy associated with the value of the field, it has no potential and it has no mass, and that's why the photon is massless. The electron field, in its low energy state, has a potential energy. So if you just try to push the field uniformly everywhere, that costs you energy, and that's a reflection of the fact that at the quantum level, the associated particles are going to have mass. So if you buy that, which you may or may not, then it all becomes very, very simple. There's a fundamental way of thinking about the electron where it didn't have any potential energy, where the value of the field wasn't giving you any contribution of the energy. But there's an interaction between the electron and the Higgs field, so that the value of the electron field does bump into the value of the Higgs. And when the value of the Higgs was 0, that was just an interaction. It was a way for the Higgs field to literally scatter off of electrons and so forth. But when the Higgs field gets a non-zero value in the vacuum, what used to be an interaction now becomes a potential energy. Because the electron field is interacting with the Higgs field, it now costs energy to change the value of the electron field. So now there's a potential energy for it, and guess what? That turns into a mass for the associated particle. You have to kind of take on faith that there is a leap from quantized fields to particles, but that is a leap you better be prepared to make, or read one of the various things I've written about it in one of my books. Okay, I'm going to once again group two questions together. Chris Shipton says, is it possible for a black hole to spin so fast it would tear itself apart? And Johann Falk says, does a spinning black hole not have a completely spherical boundary? So no and yes. Spinning black holes, well, it depends what you mean by spherical. The boundary, the event horizon of a black hole, has the topology of a sphere, but it can look like a squashed sphere if the black hole is spinning. A spinning black hole will generally have the geometry of an oblate spheroid, much like the Earth, but much more perfect than the Earth, because the Earth is kind of lumpy. It is not possible for a black hole to spin so fast it would tear itself apart, but there is a limit that you reach where it's the fastest a black hole can spin, and this is what is called an extremal black hole. So if a black hole starts to spin, there's a sort of an upper limit where it is no longer a black hole if you go past that limit, and you would get like a naked singularity or something bad like that. So in practice, what happens is you can't reach that point, right? You can start with an ordinary black hole and try to add spin to it, but how do you add spin to it? You have to throw something into it that is spinning. And so you're adding not only spin to it, you're also adding more energy to it or more mass. And you never get to the point where the spin is more important than the mass. And that's what you would have to do to reach this extremal point. But really all I'm saying here is Google extremal black holes. There are extremal black holes both in the case of spin, where you say there's so much spin it's almost trying to overcome the gravity, and there's also extremal black holes in the case of electric charge, where you say, there's an electric field that is pushing things away that is almost ready to overcome the strength of gravity. But in both cases you can't get there. That is part of the cosmic censorship conjecture, which you could also look up if you're interested. Dylan Hall says, I've watched several of your talks on finding gravity in spacetime in quantum mechanics, and also a few lectures from Leonard Susskind on spacetime being created by entanglement. Could spacetime being created by entanglement provide any explanation of inflation or the initial low entropy state of the universe? If we start with no entanglement and allow things to start entangling, what happens? They might be related, but I don't think that there is any immediate explanation from that, because it's almost implicit in your second question. If we start with no entanglement and it allowed things to start entangling, well, we can do that, But why did we do that? Why did you start the initial state of the universe with no entanglement? There's also, I think we're going to get to this later on, but whether a quantum state is entangled or not is actually not a well-posed question. You have to take a quantum system and you have to divide it into subsystems. And then you can ask whether those subsystems are entangled or not. That's a well-posed question. But entanglement has to be between two different things. So if you talk about the wave function of the universe, which is only one thing, and you say, is it entangled? That's kind of a meaningless question. So this is just a footnote to say that you have to be a little bit careful when you even say these statements. It's not that there is a statement with a state with no entanglement. There is a set of substates that are not entangled with each other. Now, it's very possible that that is the correct way to think about the early universe and its expansion. I've actually written a couple of papers that say exactly that, one on quantum circuit cosmology and the other on de Sitter space as a tensor network, a way of thinking about entangled quantum bits. And it's an interesting possibility, but it does not, as far as I know, provide any easy ways or novel ways of addressing the fine-tuning problems of the early universe. Even if you are thinking of space as created from quantum entanglement, you still have to just posit the fact that that entanglement had a certain structure at early times. Now, that might just be that none of us has thought of the right answer yet. So that's why I'm answering this question. I'm hoping that someone out there thinks of the right answer. Then you can have an acknowledgement or a citation in your paper talking about this podcast. Eli Graham says, many of us who have personally suffered homophobia in our academic and professional lives were quite moved by your comments in the last AMA regarding renaming the Webb telescope. In my own case, as recently as less than 20 years ago, I brought to the attention of the director of the school where I taught homophobic attacks against me by another teacher. The director not only refused to help me, he let me know I should be grateful the school even hired gay people. That was some improvement over earlier years when we expected at worst to go to jail and at best to lose our jobs and professional reputations for being gay. The question is, what realistically can your listeners do to get the telescope renamed? So I'm sorry to hear about those experiences, Eli, and I know that it's not just 20 years ago. Things like that still happen. Hopefully they're becoming more rare, but they're absolutely out there, and it's terrible. It's not a good reflection on us as human beings that we choose to be biased and discriminating against people in that way. So I do want to take it seriously. I do want to ask, how we can make things better. And I think that we make things better not by ignoring the problem, but by talking about it and trying to actively improve the situation. However, having said all that, if your actual question is what can we do to get the telescope renamed, and you did put the word in there, realistically, I think realistically there's almost nothing. I think realistically that ship has sailed. I would like it. So again, as I said last month, I am not a super expert on James Webb or how he behaved. My very tiny experience with reading about the claims about him made it seem perfectly plausible that he was a nasty person, especially when it came to gay people, and that he either let them be discriminated against or actively participated into it. And I think that's bad. And I don't think that we should be honoring that kind of person with telescope names. But maybe there's history there that I don't know. So I'm not trying to make new substantive claims about that. My claim is that if someone is that kind of person, we should not be naming telescopes after them. But we did. The royal we, I had nothing to do with it, but NASA named the telescope after him. And I don't see any realistic way to get the name changed just because bureaucracies are bureaucracies and they're not easy to change. So what I would say is, the telescope being named after someone who was homophobic or anti-gay is not good, but maybe we can make something good out of it. Rather than trying to think the best about how we can possibly get the name changed, which might be banging our heads against a wall, we can just be noisy about the fact that people like that should not be celebrated. And it's still a problem right now. And maybe the ongoing name stuck to the telescope can continue to be a reason to talk about that and let people know about it and not let the issue fade from popular view. Of course, I could be wrong about this. Maybe my, judging of the political winds is completely wrong and NASA's going to change the name tomorrow, which would be great if that's what they decide to do. But that is what my judgment is right now. I don't think it's the best way to expend our energies to try to get the name of this telescope changed. Brendan Hall says, what do you think about the finale of Lost? I kind of liked it, but I know many didn't. So yeah, I know that not all of you have watched the TV show Lost. I did, all the way up to the finale. So I wouldn't answer the question if I thought that it was going to be completely meaningless to people who hadn't seen the TV show. But Lost is sort of a paradigm for TV shows not ending well. And I think it's a very interesting question. When a TV show, especially a long-running network show, is kind of a unique storytelling challenge because stories are very often shaped by how they end, right? The end of a story is kind of an important thing. But when you're in season 3 of a TV show and you don't know how many seasons you're going to get, and it's not just a sitcom where you just tell jokes every week, but there's supposed to be some dramatic tension and movement from place to place, from moment to moment, from episode to episode, from season to season. It can be really challenging to set yourself up for a successful finale, especially because you often don't even know. Sometimes you're told that you're canceled after you finished doing a season and there's no real finale at all. And especially for something like Lost, where a lot of the interest of the show was a set of mysteries, right? A mystery of all the genres that you can think of has to have a payoff at the end. And so I'm pretty sure, if my understanding is correct, I actually helped interview Carlton Cuse and Damon Lindelof, who did the show, the showrunners, and I think that they didn't know what all of the things that were going to be happening were like halfway through the show running. Like they would set some things up and then try to come up with good explanations for them after the fact. That is not necessarily a bad strategy, but it can backfire. And I think that in the case of Lost, they just couldn't come up with a ending that would make everybody happy. But maybe there wasn't an ending that would make everybody happy. Another famous example of a TV show not nailing the landing is How I Met Your Mother, which is a sitcom, but it kind of in season 1 set up this big mystery. Who was the mother of the children and how did they meet? And it sort of promised an answer. But that was in season 1, and things changed after season 1, and they were stuck with that answer. They felt that they were stuck with that answer and couldn't wriggle out of it, even though it was entirely inappropriate by the time they got to the final season. So anyway, this is just interesting to talk about in my mind because I'm fascinated by storytelling, and I'm fascinated by the methodology of coming up with how to structure a story and to best tell it. And the cases when it doesn't work are just as important as the cases when it works. And, look, Game of Thrones is another example where I thought that the early seasons were some of the best television ever made. And the last season ruined it all, which was really kind of almost an accomplishment in itself. So I would like to know if there is a better theory of making finales for TV shows. Peter Bamber says, with respect to dangerous, evil, and powerful people who can make life miserable for many others, should we always await arrest and trial before deciding upon a sentence? Or is it sometimes better to save misery by means of assassination? I think this question is both good and important and far too vague to be possibly answered. It just depends enormously on what we're talking about here. I do think that in a functioning civil society, one should let the rule of law do its job. One should not take justice into one's own hands. But I also know that not every society is well-functioning, right? And it's when society is not well-functioning that sometimes you do have to take things into your own hands. Like, for an interesting case, and one I know I'm going to get in trouble saying this, but I'm going to say it anyway. The January 16th riots, right? The insurrection, the terrorist attack on the Capitol of the United States, January 6th. People make a big deal out of that, and I think correctly so. It was a terrible thing that happened. But what if we are trying to be careful and honest and say what the origin of the terribleness was? And I think a lot of people would say, well, look, they attacked the Capitol of the United States. That's a terrible thing. But, what if the election truly had been stolen? What if one party had just somehow managed to fix all of the voting machines to give themselves a victory that was not an actual reflection of what the voters had done? What if they had truly stolen the election? Now, they obviously didn't in the case of the 2020 election, but what if they had, right? What if one party had just set itself up for permanent rule by not by campaigning and winning the votes, but by controlling the voting machines? Then I think that people would have some right/obligation to protest, maybe even violently against that, right? So in some very real sense, January 6th was a terrible, horrible thing. It should live in embarrassment and ill repute for everyone concerned for the rest of their lives. But the origin of the badness isn't the attack. It's the fact that they promulgated and believed that lie about the election being stolen. That was the problem. Things follow from that are terrible, but that was the beginning of it. So anyway, which is all just to say, with respect to Peter's question, if we did live in a society which purported to be a democracy, but was not really a democracy, and all of the votes were rigged, then I think that it'd be perfectly justified to go to non-peaceful means to try to fix things. The really sad thing, of course, at the end of this discourse is that someone has to make that decision, and often the people making that decision are not very good or smart or having the best interests of everyone else at heart, which is why so many extrajudicial actions are bad rather than good. All right, speaking of controversial topics, let me group together a bunch of things. These are all follow-ups to the AMA question I had last month about a clone of Alice the criminal. So Robert Ruxandrescu says, in the last AMA, you covered a case where Alice does something terrible but dies before she gets the punishment. You argue that if a new instance of her is created, she's basically the same person so she can serve the sentence. But if that's the case, here's my proposal. I get to do whatever I want, murder, steal, etc. For each of my crimes, I create an identical copy of myself and give the copy to the authorities. This is an identical copy of myself. You can take this copy to prison to serve my sentence, I propose. This way, I serve the sentence for my crimes, while I, the original version, can roam around and do whatever I want. Konstantin Ianu, says, priority question. During September 2022 AMA, you answered positively in the below question by Anonymous, although it is contrary to intuition as accepted by you. My question is whether you would maintain the same position in the possible scenario that multiple accurate clones of Alice are created. Would they all have to be held accountable? Johann Falk says, concerning the hypothetical Alice in the September AMA, I would argue that convicting her for the crime only seems wrong if one sees the conviction as a punishment or revenge. If one sees the rule of law not as a way of getting back at offenders, but as a way of shaping society, it makes perfect sense to convict her. It assures that people acting in the way Alice did are taken care of. In best case, they are rehabilitated and helped to a better way of living their lives. Do you see any benefits of thinking in terms of revenge or punishment apart from giving any victim some kind of satisfaction? And finally, Linyu Miziara says, in the latest AMA, there's a question about a person who commits a crime, ... Now suppose the person who commits the crime is still alive and is arrested. If there are 10 identical clones of that person who don't have the faintest idea that a crime is being perpetrated, do you think these 10 people should be arrested too? So, some preliminary remarks before tackling all of these questions, which are slightly different questions about the same scenario. Remember, the original scenario was Alice is committed a crime, she is killed, but an identical clone of her is created. Should we be able to punish the clone for Alice's crimes? I chose to interpret the question, and you can interpret it in different ways, but I chose to interpret it as the clone of Alice is really an identical copy of Alice before she died. So not just a clone, not just with the same DNA, but a person with exactly the same psychology and exactly the same memories, basically an atom for atom copy of what Alice was like. I don't think, the whole point of my answer was, I don't think there's any essence of self-identity that follows the actual physical atoms of a person. That doesn't make sense to me. We're all exchanging our atoms with the environment all the time. And if I think if I literally construct a copy of someone atom by atom, they're, for all intents and purposes, they contain the same responsibilities and weight of history that the other person did. So to Linio Miziara's question, what if these other clones don't have the faintest idea a crime has been perpetrated? That's clearly not what I was talking about. I'm not talking about just clones who have completely different memories. Then I wouldn't punish them. That would be crazy. I'm only talking about punishing people who actually, in their minds, have the memories of the person who just committed the crime. You know, in their minds, they are the person who just committed the crime. And I think that if you think that anyone deserves punishment, then all such people deserve punishment. So for Johann's question, are we doing it for revenge or punishment versus possible rehabilitation and deterrence purposes? I think I'm very much in favor of consequentialism here. We should do it for deterrence and rehabilitation purposes. We're trying to make the world better, not just getting some sense of revenge. So therefore, if we're trying to deter people from doing it and we're trying to rehabilitate the people who do bad things, that's why I think that all the people in exactly the same mental state as the criminal should be given that punishment. There's no sort of metaphysical correctness to which person deserves the punishment. And then to Konstantine's question, if the person is still alive and multiple accurate clones of Alice are created, would they all have to be held accountable? Sure. Again, they're all in their minds guilty of this crime. They are the person whose mental state caused them to do this crime. And therefore, if any one of them is worth having being incarcerated or whatever, then they all are. And then to Robert's question, if I make an identical copy of myself, can I just say, well, punish them? No. The punishment should be every person who has that mental state deserves the punishment. It's not like if you punish one person, it's like, you can't punish an identical twin and say that counts if the other person's twin actually did the crime. So the whole spirit of my answer, which again, you're free to disagree with as always, but the spirit of my answer was, people do not have metaphysical essences, okay, that sort of cease to exist when they die. People are processes. People are collections of matter acting in certain ways. And if I have a collection of matter that is indistinguishable in every microscopic way from another collection of matter, both of these collections of matter look like people with certain memories, then whatever way we should treat one of those collections of matter, we should also treat the other one. That is the major point that I want to make. You can disagree about how we should treat any of them, but they should all be treated the same. Nick Nechvolodov says, why do scientists and interested parties such as myself accept the findings of experiments using the Large Hadron Collider when the findings can't be replicated with independent apparatuses? Well, I think there's lots of reasons. For one, they can, to some extent, be replicated because there's more than one detector at the Large Hadron Collider. There are two large general-purpose detectors. There's the CMS detector and the ATLAS detector. And this was, in fact, historically, crucially important to why we accepted the discovery of the Higgs boson so quickly, because both experiments saw it in exactly the same place, doing exactly the same things. So they do, in fact, use the same source of protons in the Large Hadron Collider. Okay, but still, they're doing different measurements of those protons, and that's almost a completely independent experiment. But the other is, even if there were only one of them, you would have less credence on the results if there were only one of them. But still, you would just be a good Bayesian, right? Your credences would depend on what your prior was. The discovery of the Higgs boson is something where everyone thought it should happen more or less sooner rather than later, and so we were ready to believe it. Faster than light neutrinos are something that no one believed, so people were very skeptical of, even though it's also coming out of CERN. So you just try your best to say, well, what are the chances that these people would get it right, get it wrong, whatever? Are they good? Do they have a track record? Have they convinced us that they're being honest with their backgrounds? All of these things you can do. For the more general question of how do people who are not experts choose to have belief that a certain scientific experiment is wrong is on the right track at all. I think that you have to, again, use your judgment, but we tend to trust the opinions of people who are experts. I'm a believer in expertise. Experts are never 100% correct, but they're more likely to be correct than non-experts are. So I think that the fact that all the particle physicists in the world more or less accepted that the LHC is on the right track should be taken as evidence that not it certainly is, but that it probably is. Aurea Biddle says, it may be a natural outgrowth of poetic naturalism that I often hear you remark that you don't like to debate things. You give an impression that you're perfectly fine with people believing whatever they believe and just giving your take as you currently see it. Do you ever find a time where you think it's appropriate to hash some disagreement out or dig deep into why you and someone else see things differently? Is it only in private, at dinners, with a few drinks in you? Well, I think there's a couple things going on here in this question. So I enjoyed being on the debate team in high school, and I certainly appreciate the reason why people like doing it. And I do think it's also good training, both for public speaking and for logical thinking. What it's not especially good at is a way to find the truth. It depends a lot on who's doing the debating, what the format is, all those kinds of things. When I participate in debates these days, which is rarely, but sometimes it happens, it's not really a fact-finding mission in trying to figure out how the universe works, right? It's more entertainment and inspiration for the audience. Usually, if I'm going to participate in a debate, it's because I think that I can get a message out to people who otherwise might not hear that message under different circumstances. But what you're asking in the question is sort of more about whether it's appropriate to hash out some disagreement. I mean, that's not something that I'm averse to doing at all, but that's not having a debate. I think that's a huge mistake, to conflate the idea of hashing out a disagreement or digging deeply into why I and someone else see things differently versus having a debate. A debate is very formal, very artificial. It's more entertainment than intellectual exercise. I spend my whole life hashing out disagreements and digging deep into why I and someone else see things differently. That's what academics do all the time, every day. So I do that, quite frequently. Now, having said that, you still have only 24 hours in the day. You have to choose what are the disagreements that you're going to dig into. And I would just much rather engage with people who I think are also acting in good faith, trying to learn something, trying to improve their own understanding, rather than people who are just trying to sort of demolish a debate opponent, okay? So there are people out there who are already convinced they have the right answers, and their job is just destroy the other side, and that's an exercise in which I have no interest at all. Clyde Schechter says, I'm confused about pulsars after the explanation in the Chiara Mingarelli episode. We see these objects because their rapid rotation, oblique to the axis of their magnetic field, creates electromagnetic radiation. But with this radiation going out, the pulsar must somehow lose energy. My first thought is that their rotation would slow. But then their pulse intervals would progressively lengthen, and they would not be the marvelous ultra-regular clocks they are. I assume energy is in fact conserved somehow. How does that happen? Yeah, this is a very good question, but of course, energy is conserved in this particular case. I'm well known as someone who appreciates that there are some cases in which it's not exactly true, but this is a very good case where it is. And they do slow down. It's a well-known fact that pulsars slow down over time. But two things. The slowdown is very, very tiny. So there's a quantitative question here. You can't just say, well, they slow down. How come that doesn't ruin their use as clocks? You can understand how quickly they slow down and take that into consideration when they're being used as clocks. And the slowdown is very, very tiny. There's a lot of energy available in that spin of the pulsar, and only a tiny amount of it leaks out through giving out all of this radiation. Benjamin F. says, do you agree with David Deutsch's interpretation of why we see an interference pattern in the double slit experiment? He claims we are observing a tangible photon from our universe being interfered with by a phantom photon from a parallel universe that differs from our universe only by the position of that single photon. If Deutsch is correct, is some kind of communication between worlds theoretically possible? This is an area, it's a very good question because it's an area where people who all agree that many worlds is the best way of thinking about things, like I do and David Deutsch does, can nevertheless disagree about the best way to attach words to what is going on in many worlds. I say specifically attach words because we all agree on the math. There's no distinction, no disagreement about how to use the equations, but how best to interpret them in terms of words changes from person to person. And in particular, what I would say is you can have a quantum mechanical state representing a single universe, and then you say that a certain part of the universe, a certain system within the universe, has a single quantum state, and then it becomes entangled with its environment. We call that decoherence, and then its wave function branches, and now there are two different copies of it in two different universes. That is a way of talking, but another way of talking is to sort of take the system before it decoheres and talk as if it's already two different universes. They just haven't branched yet, okay? And that's more like the way that Deutsch is talking. I don't think that's a good way of talking because in principle, things can branch in different ways, sort of along different axes. When you look at a system that is not yet decohered, that has not yet become entangled with the environment, there's no unique way to divide it up into a collection of different universes. It's just one thing, is the way that I would put it. But anyway, I kind of don't care. Like people, this is a live and let live situation as far as I'm concerned, because we all agree on what the equations are telling us. Bill Quirk says, many believe that the expanding universe requires a departure from unitarity in quantum mechanics. Do you think a departure from unitarity is needed? So what is being referred to here is unitarity is the quantum mechanical way of saying conservation of information. Unitarity is the idea that you have a wave function, it evolves from one point in time to another point in time in a way that if you know where it ends up, you can figure out where it came from. It's just reversibility in the quantum context. So the amount of information you need to specify is the same at early times and later times. Naively, you might worry that the expansion of the universe has some conflict or at least some tension with this because the universe gets bigger, there's more stuff, or at least more room for stuff, and therefore maybe you need more information, need more room to tell you exactly what is going on in that particular quantum state. So I think there's lots of things to say about this. The ultimate answer is we don't know. At face value, I think that that particular tension is overblown. It comes from our intuition, not from the equations. There's no necessary reason, just because the universe is expanding, that you need to violate unitarity. But that's not to say that you don't. You know, it's a situation where you have quantum mechanics, you have gravity. There are mysteries here, not only quantum gravity and the emergence of space and time, but as we already talked about, the mystery of the initial conditions and so forth. So here is a case where I'm open to thinking outside the box and thinking about ways to go beyond the standard quantum story. And just to mention, this would be a pretty big departure from the standard quantum story if unitarity were not part of the story. So you want to be really sure that you have a good reason to go beyond it, or at least a even better way of thinking lined up as an alternative if you want to go in that direction. Jesse Rimler says, the Russian invasion of Ukraine is a horrific crime and Russia is responsible. I believe the Ukrainians are right to ask for aid and it is right for the U.S. to supply Ukraine with aid. I also believe it is right for the U.S. to apply pressure to initiate peace talks. Critics call this appeasement, but I don't see many grappling with where this conflict is headed. One expert who does is Anatol Livin at the Quincy Institute. Under the current policy, he sees a high chance for a decades-long conflict similar to Pakistan and Kashmir, or an escalation to the brink of nuclear war. Neither would be a good outcome for Ukraine, to put it mildly. Do you think the U.S. should use its influence to help initiate peace talks? Well, it depends on what you mean by peace talks. You know, peace talks are always a good idea. I think that peace is better than war. But when you have peace talks, presumably you're trying to come to some agreement, right? You're saying, well, we'll have peace if you do this and we do this. That's where all of the hard part is. What is it going to take to have an agreement that both sides can agree to? Right now, I see essentially zero chance that Ukraine and Russia are going to agree on any peace a peace agreement. I'm just saying the word agree over and over again. That's why I'm hesitating here. But I think that their differences are too large, and that just makes sense because Russia invaded them to take over them, and it didn't work. As I will say now, what I always say here, that the United States can think whatever it wants. What has to matter the most is what people in Ukraine want. They're the ones who are being invaded, okay? So I don't see any Ukrainians asking the U.S. to negotiate a peace settlement right now. So I don't think that we really have the right to demand such a thing. Now, there is a footnote there, which is, of course, that everyone's interests are in not having a nuclear war. That is absolutely true. So I do think that we should take action if we think that there is something to be done to prevent a nuclear war that would otherwise have too high a probability. The problem with that is I don't feel that I have a good grasp on what that is, what the probability for nuclear war is, or what the actions are that would decrease it. If we set a precedent that nuclear powers can invade other countries and get what they want, I don't think that letting that precedent be set necessarily decreases the chances for nuclear war down the line. So I think you have to think past this one conflict and think about all the possible ramifications. Obviously, the Russians in power know that if they launched a nuclear attack, things would go badly for them very quickly, very soon. And so in some sense, we're still in the mutually assured destruction phase of nuclear power, although not exactly, because we're not really thinking of complete destruction of another country. Russia is unlikely to attack the United States using nuclear warheads for exactly that reason, but they might think they can get away with it in Ukraine. I don't think that they can. I think that it probably is better for the United States and every other country in the world just to emphasize the terrible, terrible consequences of anyone using nuclear weapons in a first strike for any reason. That seems to me a more stable, long-term, useful policy than trying to broker a peace agreement that the country that was invaded is not in favor of. Paul says, can science save us? I have very low expectations the world will effectively deal with climate change. If you had the proverbial unlimited budget, what technology or experts would you recommend? I don't have an unlimited budget. I don't even have unlimited or even very big knowledge about what technology would be the best when it comes to climate change. There's one very, very obvious technology, which is not even a technology. It's just stop spewing greenhouse gases into the air. That's something we know how to do. So I would prioritize that. That's not to say we can't do other things as well. I'm entirely in favor of doing technological and scientific development on ways that we can remove greenhouse gases from the air. That sounds like a very obviously good thing to do, but it's not a replacement for stopping putting them there in the first place. So as far as what the technologies are, I really have no idea. Some combination of chemistry and synthetic biology and things like that might be of help, but I'm not the one to ask about it. Chris says, if a telescope similar to the James Webb Space Telescope was at the other end of our galaxy, or halfway across the universe, and it was looking in the general direction of Earth, would it be able to determine that life, intelligent life, exists here? Probably not, is the short answer. I'm not going to give you a detailed answer here because this is a quantitative question. At what distance from Earth would the JWST be able to determine that there might be life or intelligent life here? So I don't know the answer to that question. It's really not something that this telescope is optimized for. It so happens that as an infrared telescope with very high resolution, it turns out to be pretty good for measuring spectra of atmospheres around exoplanets. Now that we know there are exoplanets, that's a very good instrument to have. But specifically figuring out whether there is life on them requires a lot more knowledge. We don't know in general terms what kind of signature life will have. We have some rough ideas, we have some guesses, but look, we had guesses about what kind of solar systems there would be, and those turned out to be half right, half wrong. If you go back to the John Johnson podcast that we did, our expectations weren't completely on the ball. So we don't even know what exactly it is we're looking for. I will say that if the telescope is literally at the other end of the galaxy or halfway across the universe, that is too far away. That's why I can definitively answer that, especially because the other end of the galaxy, you have to look through the entire galaxy, which is not transparent. There's a lot of gas and dust and clouds in the way, and halfway across the universe is just too far away. So I think that for nearer exoplanets, JWST will be able to tell us something, but it'll be hints and indications. It will not be anything cut and dried, is my guess. David Maxwell says, are there aspects of Eastern philosophy that you actively consider, research, or teach? I've re-listened to episode 160 with Edward Slingerland more than any other and would love to see some more on Eastern philosophy. So roughly speaking, no, but on the other hand, it depends what you mean by Eastern philosophy. Typically, when you say things like that, Eastern philosophy, you kind of mean ancient Eastern philosophy. I mean, I definitely read and cite philosophers who are currently in China or Japan. Does that count as Eastern philosophy, or of Chinese or Japanese or other Asian extraction, Indian, etc.? But that's usually not what people have in mind when they say Eastern philosophy. So as far as ancient Eastern philosophy is concerned, I don't really actively consider, research, or teach it, but I don't really actively consider, research, or teach ancient Western philosophy either. I will sometimes refer to it for pedagogical reasons, thinking that people might be a little bit familiar with it, or for historical reasons. There's a line of development from Aristotle through Galileo, etc., that is interesting to talk about, but I don't search the works of the ancient philosophers in the West for wisdom for our current era. Whether it's I should say about my own personal research in natural philosophy, if you want to call it that, or philosophy of physics. Now, I do think that when it comes to sort of human scale questions, you're much more likely to get something out useful and interesting out of ancient philosophy, whether it be Eastern or Western. That's just not my personal area of interest or expertise, so I don't lean in that direction. Sandeep Chitale says, can you please explain why the low entropy at the Big Bang is the cause of the direction of the flow of time? Or maybe that is not true. I can see how the corollary is true. Entropy generally increases in the direction of the flow of time, but cannot see why the converse will be true. Well, this depends on what you mean by the flow of time. At the level of fundamental physics, there's no thing called the flow of time. The equations of fundamental physics just use time as a label. It's not something that flows any more than space flows. The laws of physics relate what happens at different points of space and time to what happens at other points in space and time. I would argue that the flow of time is an impression that we human beings have psychologically. And every psychological impression that we have ultimately comes down to the thermodynamic arrow of time, the fact that entropy is increasing. This is a longer discussion, of course. I did have a couple of podcasts about it, one with Janan Ismail, my current Johns Hopkins colleague, also Dean Buonamano, we talked about it, and maybe a little bit with David Eagleman, the psychology and neuroscience of time and its relationship to entropy. We know something about the past that we don't know about the future, ultimately because the entropy was lower. We feel that we have causal influence over the future, but not the past, again, because entropy is increasing toward the future. All of this is a very long story that I'm not going to answer right now, but that's how it ties in. If it weren't for entropy increasing, we wouldn't have any conscious experiences, including the conscious experience that time is flowing around us. Jim Wade says, does an entity have to be alive to have intelligence? I like this question because it confused me a little bit. At first, because not confused me in the sense of I have no idea what the answer is, but I thought I knew what the answer was and I kept changing my mind. So my first response intuitively was, well, of course, if you're not alive, then how could you be intelligent? But then I thought about what about artificial intelligence, right? So this is clearly where I was just being too naive. I do think that there can very well be artificial things which we would not classify as alive, but we would classify as doing intelligent things. Now, do we classify them as having intelligence? At this point, what I would do I put on my philosopher hat and say that the right thing to do is not to insist on trying to answer a question, does an entity have to be alive to have intelligence, but rather taking a step back and thinking about what we mean by being alive and having intelligence. So this is usually the right strategy for these kinds of questions. When it's confusing to think about these things, The mistake might be that we're assuming there is something univalent out there called having intelligence, and another univalent, clear, rigorous thing called being alive, and we're asking, do they match up in some nice way? But as we learned from Stuart Bartlett talking about what it means to be alive, there's more than one aspect that is involved in being alive. And as we talked about many different times in many different ways, there's certainly more than one aspect to being intelligent, right? So I would say that the better question to ask is, what are the ways in which the characteristics that are associated with being alive are or are not related to the characteristics of having or not having intelligence? If you have a computer that can play tic-tac-toe and will always win, is that having intelligence? Who cares? It's an ability, right? The computer I would not classify as alive just because it could win in tic-tac-toe. But there's a relationship there that is worth exploring, but let's not be tricked into thinking these words have meanings even before we start thinking about them. Bob Polk says, if I understand entropy correctly, it is a relational phenomenon. Entropy is high only in relation to where it is low somewhere else. If this is correct, and following from this, would it ever be possible to measure the total coarse-grained entropy of the internal states of a full human being as separate from its external states using a kind of Markov blanket approach a la Carl Friston's work with the free energy principle? Said another way, could we imagine one day having a Star Trek tricorder to scan the high-low entropy reading of just one person moment to moment? So there's a lot going on here. First and foremost, entropy is not a relational phenomenon. There is, for any given system, there's different systems, of course, but a given system in a given coarse graining is just at high entropy or low entropy. Full stop. The pause there is because you need a coarse graining. You need a pre-existing way of thinking about which states are classified as living in the same macro state or indistinguishable from each other. And as we've discussed many times, this is something essentially everyone agrees on, but we have to agree on it, okay? It's not just given by nature. There are reasons why certain coarse grainings are chosen that nature suggests to us, but ultimately we have to choose a coarse graining. And once we do that, entropy is a number that you calculate, and it doesn't have to be related to anything else. For the rest of your question, I'm not quite sure where that question intersects with the ability to build a tricorder that would scan our entropy. I don't think that entropy is the kind of thing you would want to scan. What I think is true is that there are macro states, right? So there's things we can measure. If you had a tricorder, maybe you could see what configuration a person's heart or lungs were in or something like that. And that has some macroscopic shape, right? The heart is beating or whatever, the lungs are breathing. But then there's a microscopic set of things going on, and those things are going to be pretty close to equilibrium, right? If they're at a certain temperature or whatever, they are maximum entropy up to their macroscopic constraints to a very good approximation. That's not exactly going to be true. That's an approximation. It's a way of thinking about things, but I'm not sure what one would learn by thinking about the internal state of a person in terms of their entropy. Let's put it this way. I don't think the different people you meet on the street have very different entropies inside them. Chris Chattard says, there's something Chiara Mingarelli said that blows my mind, that the very first black holes might just have been pure curvature with no matter in them. You even went so far as suggesting such animals might still exist now. I'm slowly coming to the realization that you don't need matter to create a black hole, and that the GR equations allow for empty, pure curvature beasts. But then, pulling this thread leads to weird questions. Would these black holes necessarily have a singularity, an event horizon, a Hawking radiation? If the answers are yes, then following the no-hair theorem, how would you distinguish between matter-filled black holes from empty black holes seen from the outside of their event horizon? So yeah, I mean, it's absolutely possible to make black holes in general relativity without having any matter, because gravitational waves and similar kinds of distortions of space-time can effectively have energy. Right? We know that because black holes or other things that spiral into each other, the system of the binary black hole is losing energy to the gravitational waves that it's giving off. So the waves are definitely carrying energy. And that means that if you get the right concentration of gravitational waves intersecting each other, they can collide and make a black hole. That's something we can absolutely imagine happening. Having said that, gravity by itself is still a very weak force. So the chances that this happens is very small. The chances are very small. It's not going to happen very much. In the real world, the black holes that we have, we can imagine they're being created completely by gravity, but we don't think it's going to be the most common thing. Having said all that, if it did happen, you have zero way of knowing that they're the same outside. That's the consequence of the no-hair theorems. Black holes look the same given a certain amount of mass, spin, and charge. It doesn't matter what they're made out of. Black holes are not solid objects inside. They're just space-time inside. So there's no difference between a black hole that was created by gravitational waves colliding versus a black hole that was created by a star collapsing or something like that. Gary Upshaw says, in your solo talking about parallel lines, you said to launch 2 lines perpendicular to a line segment at each end of the line segment and keep them straight. Mathematically, what is straight in a curved space? Straight means what we call a geodesic. That is to say, the shortest distance path or the extremal distance path, let's put it that way. If you want more, I did write a book about this called The Biggest Ideas in the Universe, Space-Time in Motion, and I do talk about what these geodesics are. One way of thinking about it is the following, which I say this is literally right from the book. If you take 2 trees and you tie a string between the 2 trees and you pull it taut, that will make a straight line, okay? Everyone agrees. Also, if you take 2 trees and you stand at one of them and you point yourself in the direction of the other one and you just keep walking forward, you will also describe a straight line. So mathematically, those are 2 very different procedures. One, the shortest distance path, that's what you get by pulling the string taut. The other, start at a point and keep walking forward. Either one of them can be used to define what you think of as a geodesic. If the background in which you're moving is curved itself, to an outside observer, neither one of them will look straight, but they are the closest analog to what we have as straight lines in Euclidean geometry, and that's what we mean in general relativity, etc. Jim Watson says, how do we think our biology/evolution would be different if the Earth had significantly different frequency in its solar energy cycles? E.g., tidally locked with the sun, or a day that was an order of magnitude longer, or a year that was an order of magnitude shorter? And how do energy cycles influence the Goldilocks zone in the hunt for life-supporting exoplanets? This is a good question, which I'm mostly bringing up because I don't know what the answer is. I think this is the kind of thing we should be thinking about when we're thinking about life on other planets. I think that it doesn't affect how we think about the Goldilocks zone very much, but also I think that the idea of the Goldilocks has been somewhat deprecated in the thinking of exobiologists. You know, it used to be you would have a star and you would say, well, if you were too close to the star in your orbit or too far away, you'd either be too hot or too cold on your planet. These days, we realize that even here in the solar system, some of the most promising venues for life appearing are places like the moons of Jupiter or Saturn, which might have been considered in the old days outside the Goldilocks zone. So we're going to be a little bit more open-minded about where life could actually be. The thing that is relevant, I know why you're asking the question, if you have a planet that is rotating with a fairly rapid day, then even though it will be hotter during the day and colder during the night, they will both be pretty close to each other, astronomically speaking, because the planet keeps moving. Whereas if the planet is tidally locked, then one side is going to get very hot and the other will be very, very cold. There will, therefore, by continuity, be a region in between where things are more or less similar kind of temperatures as they are here on Earth. In fact, there was a whole science fiction novel written about this by Charlie Jane Anders, one of our former Mindscape guests. So you're encouraged to look that up if you want to know more about it. But at this time, it just is science fiction. We don't have any hard data about it, so we can speculate about it. I'm not very knowledgeable about whatever professional level speculations are actually going on, but it's fun to think about. Kathy Seeger says, when gravitational waves are detected with LIGO or the Pulsar timing method, how do scientists gather information about the specifics and localization of the system that produced them? Well, this is a good question, and it's a little bit tricky because gravitational waves, don't form an image. That's not how we're looking at them like we do with optical or other kind of electromagnetic radiation. But what we can do is have telescopes in different locations, pointed at in different orientations and so forth, right? You remember that LIGO has two observatories, one in Louisiana and one in Washington State. And they team up with the Virgo detector in Europe and hopefully soon some Southern Hemisphere detectors. And so as a gravitational wave passes by, it will intersect the different detectors at different times. And you can use that information to kind of triangulate where things are on the sky. Having said that, it's not very accurate compared to optical or ordinary electromagnetic things. You can't pinpoint exactly where they are. You get kind of a blob depending on what kind of signal you have. And we're trying to get better at figuring out exactly how to localize gravitational wave signals on the sky. I'm going to group two questions together. Joy Colbeck says, how do you personally visualize the interiors of black holes? And Stevie CPW says, do black holes have defined edges, and do the holes have a bottom, or are they infinitely bottomless? So I will answer Stevie's question first here, because I think that this is stemming from a misapprehension that black holes are holes. They're really not. We visualize a hole in the ground as something that has a bottom, but it's still sort of embedded in our three-dimensional space where we have holes and things like that. A black hole is a region of space-time, or it's okay to think of it as at each time it's a region of space, but it's a spherical region of space, right? There's a boundary around it, the event horizon. You can see the black hole, or you can, notice it from all different orientations, and it looks roundish, maybe oblate. And inside of it, there will be whatever made it, a collapsing star or whatever. You can't get there typically because you'll enter and you'll be crushed by the singularity. But if you hurry up, maybe you can reach the collapsing star, depending on how things are. But anyway, from the inside, to answer Joy's question, it looks the same as it does from the outside. If you pass by the event horizon of a black hole, you wouldn't notice, at least within classical general relativity, the prediction is you wouldn't notice. You might remember that there are debates about firewalls at the boundaries of black holes, but most people don't think that we're trying to get rid of the firewalls in certain calculations. So if that's true, once you enter into a black hole, you don't even notice. A black hole is defined as a region of space-time from which you can't escape. But you notice that definition is kind of forward pointing, right? You cannot escape as you move into the future. So at the moment, when you're inside the black hole, you don't even know. You know that you're following some trajectory and space-time is getting more and more curved. And in your future, probably relatively quickly, you'll be crushed as the tidal forces of the gravitational field rip you to pieces. But it's still just space-time around you. There's no sign saying you've now entered a black hole. David Boardman says, how would you distinguish scientific claims to knowledge from non-scientific ones? I don't think there's necessarily a single pithy motto that functions as a bright line between scientific claims and non-scientific ones. Roughly speaking, scientific claims are ones that stem from thinking scientifically and doing the scientific process to establish your claims. You hypothesize things, you come up with different conjectures that might be true, whether you want to call them theories or models or hypotheses, doesn't really matter. And then you test them against experience, against data, right? So there's two primary things that go on there, both of which are highly non-trivial. One is you hypothesize different things. You don't assume that you know it ahead of time, right? You don't just think you have the right answer. You admit that you don't have the final answer, and you contemplate alternative possibilities. And second is you judge those possibilities on the basis of data, whether it's observation or experiment or whatever. In other words, once again, you don't just think your way into the answer. That's what really makes it scientific, the ability to maybe be wrong, and the judging of whether you're right or wrong on the basis of comparison with your experience of the real world. Harry Udenfriend says, in a past episode, you mentioned that there was no conservation of energy in a changing space-time and pointed us to a paper that you wrote many years ago. In episode 2001, Secrets of Einstein's Equation, you discussed how an early version of the Einstein equation for general relativity was incorrect because of an error having to do with violating the law of conservation of energy. Can you please help me understand this apparent inconsistency? Sure. It just comes from the fact that conservation of energy can mean different things in different contexts once we have general relativity on the scene. There is a rule in general relativity for how energy changes in response to gravity, in response to the curvature of spacetime, the geometry of spacetime. And that rule is sometimes called conservation of energy. But it's not simply saying that there's something called energy and you add it up all through space and it's a constant, okay? It's rather covariant conservation of energy, which means that the energy might not be constant, but it varies in a very, very specific, predictable way in relationship to how spacetime itself is varying. So we call it conservation of energy, even though it's not just energy is conserved. I hope that that's accurate enough as to be illuminating, even though it might not make you very happy. Those are the words we use. It all comes down to the vocabulary we use. Again, the ideas are perfectly clear once you know what they are. Giles from Melbourne says, with Judea Pearl, from memory you both seem to dismiss the idea that Aristotle's causes were the same as those we were interested in English. Can you expand on that at all? In particular, whether the main difference might simply be that cause and effect in modern English don't exist at the same time, whereas Aristotle's examples can exist at the same time, fathers, children, bronze statue, etc. Yeah, I think that it's a slight misapprehension to think that Aristotle's four causes are causes as in cause and effect relationships that we have. Aristotle had a much more expansive notion. And of course, he also wasn't speaking English. He was speaking ancient Greek. So we have translated his idea into four causes. But, one of his ideas is the reason for which things are built, which is not really the kind of cause that we have when we're talking about cause and effects, as in the glass fell over because I swung my arm and I bumped into it. So it's just a vocabulary kind of difference. Aristotle was trying to understand change in a very general way. He didn't have modern physics. He didn't have the idea that, we have objects with locations that obey differential equations. He didn't have calculus, so he didn't have differential equations. So he just had a very different way of thinking, and he wasn't necessarily distinguishing between changes, biological changes and physical changes because we want them to happen, changes because we push them in some way, changes because there are natural ways of things changing. He wanted to distinguish between them in the way that he found most fruitful. But as I said before, most ancient philosophy is not of much use to modern physics, and his classification doesn't really carry over to the way that we think about modern physics. Casey Mahone says, whenever we put on the brakes in our cars, the energy has to get dissipated as waste heat. Do we have any idea how much processes like this contribute to global warming rather than CO2 emissions? I think there's a couple things to say. Again, this is not my area of expertise, so if you want quantitative relationships between different contributors to global warming, you've come to the wrong place. But there's nevertheless a few things we can say. For one, when we put the brakes on our cars, that's not even the greatest contributor of heat from our car, right? The engine in a typical internal combustion engine is putting out a lot more waste heat than the brakes are. But the other thing, which is probably more relevant here, is that global warming doesn't mostly come from heat. It's a little counterintuitive. You might think that we're warming up the planet because we're burning a lot of things and therefore raising the temperature. But that's not really the problem. The problem is that we get energy from the sun that heats up us here on Earth, and then in equilibrium, we give back the same amount of energy to the rest of the world, okay? But the wavelengths of light are different. We get primarily visible light from the sun, and we radiate back primarily infrared light to the Earth. So that's the origin of the greenhouse effect, is that you can put gases into the atmosphere that are transparent to visible light, like CO2. So the visible light from the sun that is heating us up just comes right through, whereas they are opaque, or at least more absorptive, to infrared light. So the infrared light that we want to radiate back to the sky gets caught in the atmosphere. If the atmosphere is transparent to both infrared and visible, then you don't get this warming effect. But if you block in some of the infrared, eventually it will get out, but it takes longer, and in the process, it heats up the planet. So it's that change of transmittivity of infrared light that is the single most important contributor here. The whole atmosphere is a very, very complex system, and that is a cartoonish kind of version of it. But the point is, it's not coming directly from us generating heat. It's from not letting the radiation from that heat escape to the outside world. Johann Falk says, considering utilitarianism and weighing outcomes against each other, it seems that putting numbers on how good or bad something is gives non-acceptable consequences, such as killing an innocent person is okay if it results in 1 million people getting an ice cream or something. What happens if we don't put numbers on outcomes, but only have them ranked as better, worse, or roughly equal to each other? Could that be a base for utilitarianism, where a lot of small good things never outweigh a single very bad thing? To me, it seems attractive, but I don't know philosophy well enough to know where such ideas would get stuck or start contradicting themselves. My feeling, I'm not really utilitarian, so I'm certainly not an expert on the best way to be a utilitarian. But I think that the feeling is that no, simply ranking good and bad things is not good enough, because the whole point of utilitarianism is to try to provide a way of comparing situations where you do have many little goods versus one big good. And the idea of utilitarianism is very much sympathetic to the idea that in some circumstances, many little goods can be better than one big good. So you need a way to be able to figure out exactly how many little goods you need to overcome the joy of one big good, right? So therefore, just ranking the goods is not going to be enough. You need a way to quantify them. That's what makes it utilitarianism. Now, that might not be your philosophy. That's okay. Maybe you're not a utilitarian and you want to think some other way. But I think that it's very plausible that there are circumstances where an ordinary person would say, yes, I like these small goods in their collective goodness better than this one singular good, okay? That's just a comparison people need to be able to make one way or the other. Even if it's not simply from adding up some utility, you have to be able to do that comparison, and simply ranking goods in some order is not going to be good enough to do that. Andrew Goldstein says, do you regard gender as a social construct? And do you think it is founded on a postmodernism view of reality, adding little to analytical or empirical knowledge? Yeah, I absolutely think of gender as a social construct. Almost everything that we talk about is a social construct. Tables and chairs are social constructs. The Earth and Jupiter are social constructs. Those are social constructs that refer to something real in the world, but before human beings, there was no such word out there as planet or table or anything like that. These ideas, these concepts, are ways that human beings divide up the world into stuff. And those ways of dividing the world up into stuff might be more or less helpful or useful for the purposes of human beings, but they are nevertheless ideas that people came up with. They were constructed by society, okay? So social construct doesn't mean made up or illusory or fake. If you listen to the podcast we did with Sally Haslinger, she will explain exactly that. So gender is absolutely one of the things that is a social construct, and that's not surprising. That's the least surprising thing in the world. So I don't know what you mean by founded on a postmodernism view of reality, adding little to analytical or empirical knowledge. I think that if anything, if you want to sort of really oversimplify the idea of postmodernism, which was sort of a collection of many different things and impossible to simplify, it was pointing out the fact that reality may or may not exist, but our ways of talking about reality are ways that we invent. And that's an important distinction, and one that should not be elided, because it gives people a way of manipulating reality, and maybe you don't want to let them do that. But admitting that it happens when you invent language is kind of an important step to not letting them do that. So postmodernists were not saying, at least sometimes, they were not saying that we can just say whatever we want. That was never the idea of postmodernism, but it was appreciating the role that human choices make and human desires and goals have when it comes to how we choose to conceptualize reality. And I think that insight can be very, very important when it's used correctly. Michael Koppelman says, can you explain what you mean when you say we quantize things? It implies to me you make discrete in some way, yet you say things like space and time are not discrete, so what's going on? Yeah, this is a very good question that just arises from the fact that the word quantize is a very, very inappropriate word. Once again, physicists using words in ways that are not always immediately transparent. So quantizing has nothing whatsoever to do with making discrete. Quantum mechanics doesn't have anything fundamentally to do with making things discrete. And if anything, it's the opposite. Quantum mechanics turns everything into waves, okay? But then those waves find themselves under certain circumstances with certain discrete set of wavelengths. Just like the waves that you make when you pluck a violin string or a guitar have a fundamental frequency and then overtones or harmonics. Same thing with the waves that we find that are wave functions of particles in atoms or things like that. So even though quantum mechanics says the world is fundamentally made of waves, there are aspects of it that appear quantized because of the specific shapes that those waves have. So when we say we quantize things, we do not mean at all we make it discrete. We just mean we take a classical system and we correspond it, it's not exactly the word, we associate it with a quantum theory. It is not a very well-defined procedure, actually. There are ambiguities there, but the idea is that we can start with a classical model and turn it into a quantum mechanical model. That's what a physicist means when it says we quantize something. Dale Echo says, I have health anxiety that causes me to have panic attacks, gives me hypochondria, etc. I love physics, but have noticed it can be a trigger for me. I was watching a video on null geodesics, and I got a sense of existential dread that led to a panic attack just from the enormity of space and limits of my mortality when it comes to exploring it. Is anxiety something you've ever had, and is there anything you can do to come to terms with how we as humans fit into something that exists at such an immense scale? Well, I think it's a complicated question. I don't want to get into advising other people on their anxieties and things like that. I think that's a personal thing that you should talk with professionals and loved ones and so forth. I'm sorry to hear about panic attacks, etc. That is a shame, and I don't really have any great way of dealing with it. I have had much milder than that worries sometimes about the existential issues that come up when one thinks about the cosmos and its enormity. And I've often told the story of when I was young, trying to go to sleep and eventually coming across the question while I was just thinking about physics or whatever, like what if the universe hadn't even existed? And that would be it. That would make me worry and feel like I was small and insignificant. But that was a long time ago. I don't really feel like that anymore. I think it is the universe we live in. I think that anxiety, if we're get to the point where we can be perfectly rational about it, there is no rational reason to feel anxious because this is our world. This is just what the world is. It's something that should be accepted. We are very, very tiny compared to the world. Our lifetimes are very, very short compared to the world. That shouldn't be a sense of anxiety. That should just be a source of anxiety. That should just be something that we learn. And I want to say, that we sort of cherish and learn to appreciate, but even that is kind of a choice, right? If you don't want to cherish it, that's fine, but it is absolutely something that we should accept one way or the other. I unfortunately don't have any great advice on how to do that. If you're struggling with it, sorry about that. I wish I could be more help. Nithin Dhananjayan says, what do you believe is the biggest societal problem today? How do you go about addressing the problem? What do you wish people did differently with respect to the problem? I don't know. Yeah, the problem with this question is that it depends on what you mean by a societal problem. I'm kind of worried about nuclear war that we already talked about before, or bioterrorism, or, a giant sun flare that taking out the entire power grid on the Earth. There's a whole bunch of things that we can worry about, not to mention global warming and things like that. But those are not specifically societal problems, I think. I think if I have to say anything, about societal problems, remember the podcast with Brad DeLong where we talked about the changes in humanity due to the long 20th century's innovations, one of which was globalization. And the others that he highlights are the modern corporation and the research laboratory. And, globalization has had many, many benefits. Brad's whole book is called Slouching Toward Utopia because the irony that he points to is the fact that we, for the first time in human history, in some sense, gave ourselves the capacity to create utopia, but then certainly did not do it in very, very obvious ways. So I think that, I don't know if this is just cheap philosophizing or theorizing, but I'm, again, certainly not an expert in this. I think that people dimly perceive that as a human race, we have generated an enormous amount of wealth over the last 100 or 200 years, and not everyone is participating in this wealth. And I'm not primarily talking about inequality. I think that there's problems with inequality, but I don't mind the existence of rich people. I mind the existence of people who are not rich. I mind the fact that not everyone is rich. That's what I mind. I wouldn't mind if some people were much richer than others if everyone were rich. But not everyone is rich. There are people in the world today who are super duper poor, even in advanced societies that should be able to do better. And it's not even sort of total amount of material goods that is the problem. It's the feeling of powerlessness that I think is the problem. If I had to pick a single societal problem, it's the fact that we have arranged things in our society where too many people feel there's nothing they can do to control their environment. They are subject to forces that are much greater than themselves. And either politically or economically or culturally, things are sort of out of their control. And this is reflected in the fact that they maybe are not doing so well off economically, but also that they're in debt, right? It's not just that they're not getting a lot of income, but even if they get income, it goes to paying off a debt, whether it's college student loans, which hopefully we're getting rid of some of them here in the US, but then we'll just get more a generation later. But other kinds of debt also, mortgages and things like that. And it all feeds into this idea that when you're under debt, you're beholden to other people and you're not in control of yourself. Jobs are changing. I do believe that it's kind of inevitable that when we have progress and economic growth, the set of jobs that are available for people to have will not be the same from generation to generation. That's inevitable and that's okay. We have to learn to deal with it, but dealing with it is hard. And when you feel like you can't be gainfully employed and make a career out of the kind of job that you grew up imagining you would someday have, that is an issue that we haven't done a lot of good in addressing. People get sick, they can't control their health care, they lose a lot of money. I think, there's just a lot of ways in which modern society has figured out to suck the resources from a large number of people and funnel it to a small number of people. And again, if that were in some John Rawlsian sense, if that process were to the better of everyone, that would be fine. But it's clearly not. And so I think that people's lack of control over their own lives in various aspects is probably the biggest societal problem we have. It leads to things like less faith in democracy, and I think that is potentially super duper disastrous. James Aitchison says, does the Everett many worlds interpretation have implications for practical reason and morality? Should I be more prudent if billions of future me's will enjoy the future I make? Well, so I don't think that Everett has many, if any, implications for practical reason and morality. So roughly speaking, the way that I would put it is, quantum mechanics means that observers, agents, human beings, people cannot predict the future exactly, okay? There is a lack of determinism in the real world. There are certain things that are just going to be probabilistic. But it doesn't really matter for purposes of practical reason and morality whether those probabilities come from many worlds or for some other interpretation of quantum mechanics. There is a metaphysical difference because in many worlds, there will be worlds in which the different outcomes all happen with probability 1, whereas in a single universe with stochastic laws, there's only a single universe and all you can say about it is the probability of certain things happening in it. But if you are either a deontologist or a consequentialist, I don't see necessarily what that metaphysical difference does to your moral or ethical or practical calculations. I think that, in terms of the most obvious example is just being a utilitarian. Clearly, it seems to me, if I branch the wave function in 2, I should not double the utility of the universe, that would mean that the most moral thing to do in the world is just branching the wave function of the universe, which seems completely silly because literally no one else would even notice it if I was like in a lab measuring a lot of quantum mechanical particles or something like that. Clearly, it would be smarter to divide the utility in pieces and divide it up between the different universes, just like we divide energy or something like that, in which case the total energy is conserved. Likewise, the total utility is conserved when you branch the wave function of the universe. And to that extent, there's no effect that many worlds has on practical reason and morality. Thought of it another way, so I'm a little confused, by the way, James, when you say billions of future me's. I'm not exactly sure what that means, but I think I don't like it. I think that this is saying, again, a single universe ontology, you're thinking of your future self, and many worlds has big metaphysical implications. It says there are many future people who count your present self as their past self. But they're different people. Again, this is what I always say about many worlds. All of those people are different. But they're all thinner in a very quantitative sense. The worlds they live in are tinier fractions of the net total of the world out there. So I don't think it's a good thing to think of them as billions of future copies of yourself in a way that is distinguishable from many possible copies of yourself that have different probabilities of experiencing different things in a single universe version of quantum mechanics. Having said all that, as I say in Something Deeply Hidden, if you want to try to cook up something, to cook up a version of ethics or morality for which many worlds does have an implication, you can do that. And the way that I came up with is, imagine that you had some ethical principle that said a certain kind of thing is just absolutely bad in the sense that it's not okay if it ever happens. Like, this is a completely silly example, but what if when you measure the spin of a particle that would be 50-50 in conventional quantum mechanics, you had an ethical principle that if anyone ever measured spin up, that would be an entirely impermissible moral disaster to measure spin up. Obviously, this is a bad example, okay? But keep that in mind. The point is that if that were your moral principle, you would behave differently in many worlds versus a purely stochastic version of quantum mechanics. Because in the stochastic version, you would say there's a 50% chance this impermissible thing happens and a 50% chance it doesn't. So that's bad. I don't want to do it, but okay, at least there's a 50% chance that it doesn't happen. Whereas in many worlds, there's a 100% chance that the bad thing happens in one world, and a 100% chance it doesn't happen in another world. But if your moral principle is, if it ever happens, that is an impermissible disaster, then many worlds says, don't ever measure that spin, okay? Whereas in the stochastic world, there's only a 50% chance that this really happens, this terrible thing. Again, this is entirely cooked up just to give you a way that many worlds could matter, and that's why I think it doesn't matter. But maybe, I don't know, the future theory of morality lets us realize that it is actually like that somehow, and many worlds does matter. Jessica Napier says, what was your upbringing like? You seem to have an endless amount of curiosity and fearlessness about trying out ideas, making guesses and adjusting and so on without your ego getting bruised along the way. I think my ego gets bruised all the time, but I do think it's important, Jessica, to make guesses and adjust and so on. And she continues, as a primary school teacher, these are attributes I try to encourage in my students, but sometimes they want to be told what to think, or they're so afraid of getting the answer wrong that their curiosity shuts down. Did the adults in your life play a role in bringing out these great qualities? I don't know. I had various great, helpful adults in my life, but I think that this particular aspect of not being too afraid of being wrong, as far as I know, this was just my idea, not anything that I got as a particular lesson from anyone else. But, I don't want to sort of personalize it too much in the sense that I don't think that the right way to get out of it, I agree with the problem. I agree that students are afraid of getting the answer wrong. They want to be told what to think, etc. These are absolutely true aspects of students, and I think that it would be better if we could somehow encourage them to do otherwise. But I don't necessarily think that the right way to conceptualize how to do that is let's get the right adults telling them to do it. The system is kind of set up to make them think that way. We give kids grades, and those grades can be very impactful. They're high stakes. So it's not wrong for the student to care about their grades, right? And if they care about their grades, they don't want to be wrong. That's what we train them to do when they're very, very young. They don't know any better, and they're happy to say a lot of things and learn. As Judea Pearl said, babies are just out there making causal maps of the universe. That's what they're doing. They're touching things and doing experiments and learning about things. And that gradually becomes harder to do. And a lot is it because we don't reward them for doing it. So what I would, if this were my goal in life, to improve our upbringing of kids in the way to make them more curious, what I would do is not look for more inspiring role models from adults, but to adjust the system in ways that rewarded curiosity and play without punishing being wrong as often. And I say that, without too much conviction, because I know that grades are important and they're motivating as well as fear-inducing. And also, not everyone can get into graduate school, so we need some GPA to look at and things like that, right? So there are roles for these evaluations. It's okay to evaluate people. It's not okay to make them afraid of failure. And I don't know how to thread that needle perfectly well. Tomasz Gajosz says, I'm excited about the launch of the biggest ideas in the universe. I'm just reading the simple harmonic oscillator part, where you start with a ball rolling on a frictionless parabolic valley, but by equation 3.8 you jump to talking about oscillating particles and state that the initial velocity will depend on the mass of the particle represented by the oscillator. You could relate it to the initial position and potential by thinking about energy conservation. In our ball in the valley system, the maximum speed reached at the... Okay, I'm not going to read the whole question. It's kind of hard to keep in your mind unless you've read the book. The point is, I can give the answer very, very quickly. I'm just trying to help out the book readers here. There's a section in the book where I talk about a ball rolling on a hill, okay? And if it's literally a ball rolling literally on a hill, you calculate the potential energy in terms of the height of the hill. And there's a formula for the potential energy. The potential energy is the mass of the ball times the height of the hill times the acceleration due to gravity, mgh. I got the order of those wrong, but you know what I mean. H is the height, g is the acceleration, m is the mass of the particle. And then the kinetic energy is 1/2 mv squared. So the total energy has just an overall factor of m out there, and it actually turns out not to matter. So that's where the origin of this question is coming from. Why should it depend on the mass? But very often, physicists will change variables to something more convenient. So rather than writing mgh, mass, acceleration due to gravity, height, they will just write v of x. Okay, so they're absorbing the mass and the acceleration due to gravity times the height into one thing called the potential at every point. And then the potential energy at every point itself doesn't depend on the mass, okay, because we absorbed it in there. So when you're writing in terms of those variables, you cannot simply take out the mass from the whole thing and treat it as an irrelevant external parameter. It will enter into your equations. So you can choose to do it that way or not. It's up to you, but depending on which variables you use, the answer will or will not depend on the mass in some way. Okay, I'm going to combine two questions together. Nicholas Chapman says, why is the electron charge quantized? And Francis Day asks, I listened to a podcast about the electron today. That is great that people are listening to podcasts about the electron. That's my editorial comment here. One of the physicists on it said that the question of why the electron has a negative charge that exactly matches the positive charge on a proton is still a mystery. And it struck me that the other time this question is relevant is at the Big Bang, where the matter-antimatter asymmetry problem is not yet explained. Is there any chance that these two things could be related? Could positrons have become quarks and balance things out? Well, so let me answer first the why is the electron charge quantized question, because it depends on what you mean by quantized. I mean, obviously, every electron has the same charge. That's one aspect of quantization. And that's actually very answerable. It's because what electrons are is excitations in the electron field. There's a famous story about Richard Feynman and John Wheeler, where Wheeler calls up Feynman in the middle of the night and says, I know why all the electrons have the same charge. It's because they're all the same electron. And this was the origin of his idea that you could think of positrons as electrons moving backward in time. People love to tell that story, but it's not right. Wheeler was not correct. It's not all the same electron. They're all vibrations in the electron field. Feynman and Wheeler were kind of wondering in the back of their minds, these are still the early days of quantum field theory, whether they could do better than quantum field theory and replace it with a theory of particles. But these days, no. We know that it really is the field that is driving everything. And the reason why all electrons have the same charge is because they're all part of the electron field. But that is not enough to tell you why the charge in the electron field is exactly equal in magnitude and opposite in sign to the charge in the proton field, or the combined charges of the two up quarks and the down quark that go into making a proton. That is something that we don't have the once and for all final answer for. In the 1970s and 80s, when a lot of work was put into developing grand unified theories, where you would unify the electroweak force with the strong nuclear force, one of the nice things about those theories is they could provide an answer to why electrons and protons have the same but opposite charges, because they were part of a unified story to tell. But we don't know if grand unified theories are true. Maybe they're not. So there's other possibilities out there. There are something called anomalies in the gauge symmetries of particle physics that seem to give you relationships between the charges of different particles. I forget whether that's enough. I don't think that's enough to say that protons and electrons have to have the same charge, but there's a relationship between them if you want the anomalies to cancel. But that's only one sort of relationship, so you could add new particles in there and change it in different ways. So I think that the answer is we're not sure yet about that. As far as matter-antimatter asymmetry, I don't think that that's the same problem. They may in some way be related, but only because they're problems that we don't know the answer to, and we don't know what the initial conditions were at the early universe. Both grand unified theories and other theories of beyond the standard model particle physics, like neutrino masses and so forth, may end up being very important for explaining the matter-antimatter asymmetry. And they may also be important for explaining the charges on the proton and the electron. Beyond that, I would not want to say very much specific. Lars says, I listen to several popular science podcasts and also follow a few YouTube channels. It seems to me that most of this content is within the realm of physics and natural sciences, with some philosophy and maybe AI research here and there. What do you think it is that makes these topics so appealing and interesting to the general public? I mean, I want to say that because they're really cool. Physics, natural sciences, philosophy, AI research, but many things are cool, of course. If you look at YouTube or podcasts overall, science of any sort is not dominating anybody's list, right? There's a lot more murder or self-help podcasts out there than there are science podcasts. I mean, maybe the question is different kinds of science, biology or chemistry or material science versus cosmology, big questions kind of things. And part of it is you have to give the people something interesting. You can't just complain that there's more of one than the other. I know you're not making this complaint, but there are people who complain, why doesn't my particular subfield of science get more attention in the popular media? So you got to kind of go out there and do it. It might be true, I don't actually know that this is correct, but it might be true that the kind of people who like those kinds of science are also oriented or at least interested in popularizing it, right? Sharing it broadly. That might be part of it. I don't know. The other part might just be that you don't need a lot of background to appreciate questions like, where did the universe come from? Or will a computer become intelligent someday, right? Those are easy questions to ask. It goes back to physics being simple in some way. So I don't know. I don't actually complain about this kind of thing. I don't worry about that, especially because I think that in terms of getting new people interested in science, it almost doesn't matter what kind of science they become interested in. You can ask a lot of graduate students doing physics what first got them interested in science, And even if they're doing atomic physics or plasma physics or whatever, it might very well have been The Elegant Universe by Brian Greene talking about string theory, or just watching science fiction shows or something like that. It's the idea of science and chasing down these big questions and trying to answer them that gets people interested, almost irrespective of what the actual subject matter is. Douglas Long says, "We just rolled in to visit my son in Pasadena, just north of Caltech. This is the first time we will walk across the campus for Pete's without the possibility of running into you. So I can now ask this question. Just wondering if that were to happen, would you welcome a hello from one of your patrons? I always planned on just giving you a curt nod if it ever happened." Sure, I'm very happy to say hi to anyone who supports Mindscape on Patreon. I'm even happy to say hi to those listeners out there who don't support on Patreon. That's how generous I am. I mean, I'm probably doing something and don't have a lot of time to chit-chat or discuss one's favorite interpretation of quantum mechanics, but certainly very, very happy just to say hi. And look, I greatly appreciate that there are listeners and that there are supporters. I think it's wonderful, and I try to do the best job I can so that you enjoy it, and very happy to get feedback on that. Olafur Skuli Magnusson says, "Does antimatter appear naturally here on Earth?" Yeah, absolutely. I think that sometimes people get an idea that antimatter is mysterious or hard to find or something like that. It's really not. Antimatter was first discovered by Carl Anderson in cosmic rays, but the cosmic rays themselves were not antimatter. They were high-energy protons that are cosmic rays coming down and hitting the atmosphere and creating a shower of elementary particles, some of which were positrons, anti-electrons, and some of which were muons and anti-muons also. So that's one obvious source. Of course, in some sense, that's coming from the sky, but many kinds of radioactivity give off antimatter particles. There's the rare event where you can give off a positron, but it's extremely common for radioactive decays to give off antineutrinos. So yeah, antimatter appears here on Earth all the time. It doesn't last very long, any individual antiparticle. If it's a neutrino, it will just escape away. If it's a positron, it will hit an electron and annihilate, but they're definitely produced. Jason K. says, "Gedanken experiment. You are a living being whose entire existence is within a black hole. The everyday reality of your universe is ruled by quantum physics. Would an equally advanced civilization, I suppose this means, as ours, discover classical physics and four-dimensional space-time outside the black hole?" So, two things. One is, as we said earlier, there's plenty of classical physics inside the black hole. There's absolutely no reason to think that somehow the world is more obviously quantum mechanical just because you're inside a black hole. You wouldn't even notice if the black hole were big enough. You would have an end date, you have an expiration date, much like you would if the universe were collapsing to a big crunch. But the other thing is, in some sense, would you be able to extrapolate to the outside of the black hole? Well, sure. For one thing, you can see it, right? Light can come in from outside the black hole and be observed by you in your telescope. You are inside the black hole looking to the external world, and you can see outside the black hole, no problem. You just can't get there before you hit the singularity. The final thing is that, in some sense, this is what we do all the time in science. We discover local laws of physics and we extrapolate them to the regimes that we don't see. In some sense, it's like talking about the multiverse or something like that. We have laws of physics, equations that we believe and trust because we test them within the regime we can test them. And then we say, if they continue to be true in other regimes, then it implies this other stuff, right? So four-dimensional space-time outside the black hole would be part of that. Of course, again, it's not exactly the same in this case because in the black hole you can just see it directly, but the idea of believing the laws of physics that you believe are true is one that applies in many different sets of circumstances. Jonathan Goodson says, "I've devised a different quantum interpretation that, in my uneducated opinion, addresses the measurement problem, explains the two-slit experiment, and cures world hunger." Okay, maybe some exaggeration there. "I realize that the odds are overwhelming that the interpretation is mistaken, but I'm still eager to have it reviewed by someone knowledgeable. I have no personal contacts in the world of physics or academia. I'm not asking that you critique the interpretation, since I don't think that's what you intend AMAs to be, but if you were me, what strategy would you adopt to find a professional who'd be willing to look over your idea?" honestly, when people ask me questions like that, I usually just point them to the internet. There are absolutely forums out there. Quora is one. There's certain forums on Reddit. There's just physics forums. If you just go to Google and look for physics forums, there are people who are interested in talking about physics. Of course, it's the internet, so you can't always believe that your interlocutor is on the ball. You'll get a wide range of people with different levels of expertise, but you might find people who are willing to talk to you and discuss the idea. But let me say the other thing, and I hope this is taken in the spirit in which it's intended. What are the chances that if you're not an expert, you have come up with a good quantum interpretation that none of the experts have come up with, right? Are you reading Foundations of Physics and the British Journal of the Philosophy of Science? Have you figured out and learned about all the known interpretations of quantum mechanics, whether it's many worlds or pilot wave theories or cubism or objective collapse models or relational quantum mechanics? Have you been reading the literature and listened to talks online about people debating the relative merits of these things? If so, then it sounds like you are pretty educated. And if not, then why are you asking experts to critique your interpretation, right? I mean, you haven't done the work to understand what is already understandable. So, I think that a lot of people faced with problems in physics make a leap to saying, well, I'm going to solve this problem in physics, which is fine. It's a good ambition to have, but it's much more productive to first learn everything you can, right? To really do the work. If you're going to ask other people to do the work to understand your stuff, then your responsibility is to do the work to understand their stuff first. And so I think that once you do that, you'll be able to critique it yourself, which is much more useful than asking random people on the internet to do it. Keith says, J.J. Redick's podcast has had some great interviews with the 76ers stars, Joel Embiid, and recently with former star Ben Simmons. J.J. pointed out that Ben Simmons, despite the extreme criticism he has faced for his shooting, led the NBA by far in three-point shot creation for others, on top of being an elite defender and all the other things that are not specifically shooting. What are some of the analogous phenomena in physics research where some individual metric like citations is important, but maybe overweighted at the expense of other contributions, mentoring, good public communication, etc.? Yeah, that's a great question. I think that the way that it would be more, you phrased it in a very clever and fun way, the sort of more standard down-to-earth way of phrasing it is, what kind of academics are good citizens, not just producing their own work, but helping other kinds of work. And I think that that extends, like you mentioned, mentoring and good public communication, but even to the writing of papers. I remember once there was a study that was done in astronomy. This was decades ago, but it was who was acknowledged the most, who was given thanks the most in the largest number of papers published in the Astrophysical Journal, right? I do think that that is extremely important as part of the system that creates good scientific results. I think that we far overemphasize the specific contributions or achievements of this or that individual person and completely forget about the huge support system that goes into doing this, whether it's having your own students in your group, your postdocs helping you, having colleagues that can help you, etc. So I think that when it comes to promoting, hiring, acknowledging the work of scientists and other kinds of academics, it would be better, we'd all be better off if more effort were given or more consideration were given, attention were given to being a good citizen, being the kind of person who not only does good work, but makes other people's work even better. Having said that, it's really hard to quantify, right? I mean, it's even hard to quantify research success, but at least citations are something. It's very far from perfect, but at least it's a little bit of a measure on how much impact you've had. Whereas helping other people to come up with high citable papers is something that's very, very hard to quantify. So I think that you just have to face up to the challenge of that. Okay, it's hard to quantify. Still, you got to do it. You got to try to do it. I think that is very important. And, that is one of the reasons why when people are hired or promoted, et cetera, we don't just look at their list of publications and their citations. We also ask for expert opinions, letters of recommendation or letters of evaluation from people who are well known in the field. And they can say things like, this person has been a good citizen, making things happen in various ways. So I agree with the spirit of the question, which is that helping others in those ways is a crucial part of getting science done at the top levels. Marco Tauser says, as I understand it, decoherence is nothing more than entanglement run amok. Moreover, little things decohere all the time as they entangle with their environments, and yet wise people, yourself included, talk about entanglement being a precious resource, usually in the context of quantum information. What gives? How can it be precious and also common as dirt? Yeah, this is a very good question. I'm glad you are asking it. And the short answer is decoherence is not just entanglement. Decoherence is entanglement with the environment, okay? So the background picture we have here is that there are systems where we can actually exactly talk about what part of the system is doing what thing. And then there's the environment, which is sort of everything else in the universe that kind of is the noise in the background that you keep bumping into. The air in the room, the photons in the room, various things would count as the environment. It's a little bit subjective, what counts as the system, what counts as the environment. But I think the way to think about it is for different problems you would be interested in, you might be able to pinpoint for this context, here's the system I'm thinking about, here is the environment. So decoherence is not just entanglement. Decoherence is entanglement with the environment. And typically, if you're doing things in the standard way, the environment has many, many, many degrees of freedom. Right? The photons in a room, there's a lot of photons out there. And what that means is that when you become entangled with the environment, that's usually an irreversible process. There are too many moving parts in the environment so that you can't undo it. You cannot control it. You've lost control. It's like scrambling an egg. Hard to unscramble the egg, right? And in fact, literally the entropy goes up when you become entangled with the environment. So that's a kind of entanglement, decoherence, that is irreversible, and this is why in the many worlds version of quantum mechanics, it represents a branching of the wave function, because different parts of your system are now separated from each other by being entangled with their environment. Whereas the entanglement that is considered to be a precious resource is entanglement between different parts of your system, different parts that you're trying to keep track of, that you're crucially interested in. So if you have a quantum computer, you have some qubits, okay? And you're supposed to be able to read out the qubits. It's not Avogadro's number of particles just bumping into each other in some thermal state. It's a specific set of variables that you can measure. And you want those to be entangled in a very specific way that you can then control, manipulate, run an algorithm on the quantum computer. And one of the deep issues here is that we don't generally get into talking about this, but remember earlier on in the AMA, I mentioned that whether a state is entangled or not depends on how you divide that state up into subsystems, right? And so it's not like there are entangled states and unentangled states. There are subsystems of states that are entangled or not. And in fact, it goes beyond that. If you think of the environment as basically performing a measurement, okay, which is, again, what many worlds would do, and I think that what any other, even if it's not many worlds, any sensible version of quantum mechanics would think of becoming entangled with the environment, becoming decohered as effectively performing a measurement. Then you can break the entanglement that other subsystems have. Once you do a measurement, if you have, two particles that are entangled with each other, okay, and so let's say their spins are anti-aligned. So you don't know what either spin is, but you know that the spin of one is opposite the spin of the other. But then you measure the spin of one. So now it is not entangled with the other one anymore. You have broken that entanglement. It's still correlated because you've measured the spin of one and you know what the spin of the other one is, but there's no entanglement because the whole thing is not in a superposition anymore. You just have one spin pointing in one direction, the other spin pointing in the other direction, no quantum mechanical connection between them. So that process of becoming entangled with the environment actually breaks the entanglement between other parts of your system, and that can be bad if you're trying to keep that entanglement there as part of a quantum computation or something like that. Tarun says, congratulations on the recent launch of your new book. I imagine that this is This is perfectly suited to someone like me who wishes to go beyond the popular science treatment of modern physics but did not study the subject at university. However, I read the first 2 books in Leonard Susskind's Theoretical Minimum series on classical mechanics and quantum mechanics, and I'm currently working my way through the 3rd on special relativity and classical field theory. How do your biggest ideas books compare, and would you still recommend them to someone in my position? So unsurprisingly, yes, I would still recommend them. I know Susskind's books very well. Leonard Susskind, former Mindscape guest. I even blurbed at least the first one, maybe others as well. Others as well. I'm pretty sure that's true. And they're great. I can highly recommend them. Lenny is a master of the material, but the spirit of those books is a little bit different. I mean, they're similar to my books in that they're trying to teach you physics from the ground up and they do the equations. But Lenny's is more like a conventional physics course, just sort of softened up a little bit for people who are not necessarily going to become physics majors or something like that. They're still teaching you a lot of the down-to-earth manipulations that you would need to try to solve the equations and all that entails. Whereas my books are really just trying to get to the good stuff, just teaching you the ideas, not trying to teach you the manipulations you would need to be a professional physicist. And therefore, we get to go much faster. we can, on the one hand, dwell on some of the deep philosophical issues, and on the other hand, just still get very far very quickly. So I think that Lenny has a new book coming out in the Theoretical Minimum series on general relativity, which is like book, 4 or 5 in the series. I'm not sure. But general relativity is in my book 1 because we can just go much faster. And so there's only going to be 3 books in mine. There will be plenty of things in my book that are just not going to be in his, again, because we can go faster. So I'm not dwelling on how to diagonalize a Hamiltonian or anything like that. In book 2, we're just going to do quantum field theory and renormalization. And in book 3, we're going to do complexity and emergence. And it's really just giving you a glimpse of the ideas of modern physics in the quickest and most digestible way. So if you think that's interesting, I'd recommend buying the books. Peter Gallet says, we hear a lot lately about the dangers of human extinction, but the world is rife with human anguish and agony. If extinction would mean an end to suffering for all time, is there a case to be made that extinction might be the more moral choice? There's always a case to be made, but I think that in this case, the case is pretty terrible. For one thing, I don't agree that the world is rife with human anguish and agony, at least if that's the end of your sentence. I think that the world is also rife with joy and triumph and human accomplishment. And furthermore, there might be a lot more of that in the future. I have a good time making a podcast. I don't want the world to end and humankind to be extinguished so that I can't make my podcast anymore. That is one very, very tiny consideration, but it's the kind of consideration that you multiply by several billion, and I think there's a very good case to be made that extinction would be bad. If nothing else, even if people really were all miserable, extinction removes the chance of any change in the future, right? So even if you were much more serious about saying that humankind had just, no joy in it whatsoever, I think that it would still be true that you should not extinguish it because maybe that will happen further down the road, and you don't want to eliminate that possibility. Sandro Stuckey says, if the large-scale structure of the universe arose out of quantum fluctuations near the Big Bang, does that mean, according to the many worlds interpretation, that there's an infinite number of universes, each with a different large-scale structure, corresponding to a different quantum eigenstate? And if so, what caused the superposition of all these states to decohere? So I want to clean up a couple things here. It's a different quantum state. It's not a different quantum eigenstate. Not all quantum states are eigenstates. Eigenstates is a specific kind of quantum state that has a definite value of a certain observable quantity. So you can have an eigenstate of energy or an eigenstate of position, but the generic state is not an eigenstate of any familiar, well-known observable. So that's one thing. But the basic answer is yeah. Oh, sorry. The other thing is it might not be an infinite number of universes. There could be a lot of universes, but whether the number of universes is infinite is a technical thing that we don't really know about. But the basic answer to the question is yes. If you believe in many worlds, and you think that the origin of cosmic perturbations is in quantum fluctuations in the early universe, as it would be true in the inflationary universe scenario, but also in other scenarios, then yeah, there absolutely are other universes out there where the distribution of quantum fluctuations was different. So the distribution of specific galaxies and stars and things like that is completely different from branch to branch of the wave function. So what caused superposition to decohere? It's the same thing as always does. The environment, whatever you count that to be. You could just say all the photons in the microwave background. There you go. That's an environment. You're not keeping track of all those photons. I actually wrote a paper with Kim Boddy and Jason Pollock on how this works out during inflation, how things decohere with each other, because as usual, lots of physicists are kind of slapdash in their applications of quantum mechanics. So in the discourse about inflation, they often treat different regions with different values of quantum fluctuations as sort of as if they were magically being measured by something, right? But they're not, of course, being magically measured, but they are decohering. So you have to sort of sit down and think about what is decohering and what is the environment. And there's various things that act as an environment. Modes of all the quantum fields outside your horizon can act as an environment. Short scale modes of photons and things like that inside your horizon can act as the environment. So there's various things that will cause you to decohere. At some point, one should mention that there is something called the decoherent histories formalism that was created by people like Griffiths and Omnis and Hartle and Gell-Mann. And what they try to do is address this fuzziness that arises in thinking about decoherence as being entanglement with the environment under conditions when you don't necessarily know what the environment is. So they give a more general and robust definition of what it means for different histories of the universe to decohere that doesn't require a specific carving out of the environment versus the system. They will get the same answers in the cases where it works, but it's a little bit more general, high-powered formalism. So it can be done if that's what you want to do. Frank Lehman says, what is it about the universe that the second derivative of position tends to be really important, but the third derivative not so much? Basically, the moment you introduced me to jerk, which is the third derivative of position, I wanted to know why I haven't heard more about this concept. Same goes even more for snap, crackle, and pop. Those are the fourth, fifth, and sixth derivatives with respect to time. Can you imagine a physical application of crackle that isn't trivial or designed just to get a bewildered chuckle out of undergrads? So there's two different questions here, but they're both good, so I'm gonna tackle them both. For the latter question, physical application of crackle, I sort of make fun of snap, crackle, and pop, and I did that in the Biggest Ideas in the Universe videos, and several people chimed in the comments and correctly pointed out that even if physicists don't care about this, engineers often do. There's sort of different physical effects in, a train or an airplane or whatever, depending on not just the acceleration, but all the higher derivatives of acceleration also. So I absolutely can imagine physical applications of these ideas. Now, the deeper question about why the universe cares about the second derivative of position, namely the acceleration, but not the third derivative, the cheap answer to that is the laws of physics, as Isaac Newton handed them to us, and more or less we're following in his footsteps here, say that the state of a system is given by the position and the velocity. So if you can have a formula that helps you figure out the acceleration, you know everything, right? And that formula for Newton is F equals ma, force is mass times acceleration. You don't need anything beyond that. But you do need position and velocity, and the reason why is because there's no absolute position or absolute velocity, right? Everywhere in the universe, the laws of physics are the same. At any velocity relative to something else, the laws of physics are the same. That is not true for acceleration. Acceleration is the first of these quantities where you can absolutely measure it, right? You know whether you're being accelerated or not, according to traditional classical physics. Now, you're still allowed to say, okay, why is traditional classical physics like that? That's a more subtle question, and I think that the thing to say is, here's the way in which it is subtle. If you have a set of differential equations, so equations like the equations of motion for classical mechanics, you can always write them as purely first derivative equations. You never have to use the second derivative. And in fact, this is exactly what Hamiltonian mechanics does. So rather than saying you have x for position, and x dot is velocity, and x double dot is acceleration, where dot means derivative with respect to time, you can just say, I define y equals x dot. And then, rather than having x double dot is the acceleration, y dot is the acceleration, and all of your equations for both x and y have no more than first derivatives in them now. There's no second derivatives anywhere. So you can absolutely do that for ordinary classical mechanics. You never need second derivatives. You can write them all as first order equations, first derivative equations. But then the question is, why is it also useful to write them as equations with second order in derivatives? And that's basically the question of why do we live in position space, not in momentum space? Why do we treat position and momentum so differently? That's a highly non-trivial question that nobody knows the answer to. I have some ideas, but it's one we usually just take for granted rather than trying to solve. Suraj Rajan says, what are your thoughts on the idea of humanity evolving into virtual minds proposed by HBO's Westworld? I haven't followed Westworld that much since the first couple of seasons, so I'm not quite sure what is happening there. You know, I'm a believer that consciousness can arise in all sorts of different substrates, so I have no trouble believing that artificial intelligence could become conscious. I do have trouble believing that humanity can evolve into it. And that's not because of any mystical specialness of humanity. I think that once you are an artificial mind or a virtual mind, you will be different than what you and I think of as human. I think that human beings are very, very not controlled, but affected, determined, embedded in the fact that we have bodies, okay? Having a body is crucial to being a human being. The body not only embodies our minds and our various metabolic processes, it also gives us motivation to do various things. We get hungry, we get thirsty, we get tired, right? If none of those issues are there in the virtual reality, then we're a very different thing than we actual human beings are. So I really think that people haven't thought very deeply about what kinds of minds there would be in the virtual world. You can always try to mock up a simulation of hunger and thirst and bodies, etc., and try to make it as human as possible. But would you want to do that? I mean, maybe you don't want to do that. I don't know. Maybe that's just a bad idea and you could come up with a better system. So I am not sure that the TV/movie/novel idea that we human beings are going to basically transport ourselves more or less unaltered into a virtual realm is the right way of thinking about it. Paul Hess says, do you think there's a rock bottom fundamental makeup of the universe, such as perhaps the quantum wave function or some layer below that? Or do you think it's more likely that there is no most fundamental construct, and instead, as the saying goes, turtles all the way down? Well, I do think that there is a fundamental rock bottom makeup of the universe. There's the universe, whatever that is. I don't know that we're necessarily close to figuring it out, or we might be. It might be some kind of wave function. It might just be quantum mechanics is the right fundamental framework, or it might not be. But there's something the universe does, right? And we might be close to figuring out or not, but in principle, it's figure outable, I think. I think that the universe has given us no indication whatsoever that it is somehow unintelligible. Exactly the opposite. The universe has really revealed an enormous number of its secrets to us. So I think that whatever the description is, I'm not going to say when we're going to find it, but I think it's out there lurking somewhere. Ezra Parzabok says, not sure if you've discussed this important topic publicly, but how did the cats do with their move to Baltimore? I'm pretty sure I have discussed this topic publicly, so I'm not going to dwell on it. But, you know, the cats are doing fine. Caliban, the boy kitty, adopted right away. He's very, very chill. Ariel, the girl kitty, is much more high-strung. It's taken her a long time. She was traumatized by the move, and she hid under various blankets and things like that for a long time. But now she's almost completely back to normal. Sadly, we're in an apartment, and we're going to move again into a house, and so there's going to be one more bit of trauma. But the house is so nice and has so many big places to run around. I'm sure that both kitties are going to be very, very happy once that move happens. Rob Patro says, if I am interested in trying to popularize computer science and spread the good news to a broader audience than the students at my university, what advice do you have? Why do you think physics has been so successful popularization while CS has paled in comparison? So I guess I already did say a little bit about this just a minute ago, but I don't know. I think that CS has been pretty good at popularization. I think that people are pretty aware of AI and various puzzles in computer science and things like that. I don't know how to compare them in any objective way. If you're interested in trying to popularize, again, there's a million different ways of doing it. I don't think there's any one right format. I think that part of the trick to popularization is that different people will respond differently. Some want to see things on YouTube or whatever. Some want to listen on podcasts. Some want to read. Some want to do demonstrations. Some want it short and simple. Some want it long and complicated. And you need that kind of pluralistic approach to be successful. I have no special advice along these lines because, I'm actually, even though I do a lot of communication, etc., I am not an academic expert in the science of communication. I think that is a field that someone can be an expert in. I just kind of do what I like doing and hope that the chips fall where they may. So I'm not always very helpful to giving other people advice about how they can do it. I do think that, maybe there's some reflection there, do the things that you would have found interesting, right? Do what you want to do and your passion will come through and people will catch on to it. Doug Dugan says, is there any area of research that you think should receive more attention? Conversely, do researchers spend too much time on any one topic, e.g. the search for subatomic particles? I don't think people spend too much time on the search for subatomic particles. I think that if you go into typical physics departments, that's a minority pursuit. As we've been talking about, not every subfield within science gets equal publicity. So you hear a lot about the search for subatomic particles, but that's not what most working physicists are involved in. I certainly do think that there are fields that should receive more attention, namely all the ones that I'm interested in, whether they are foundations of physics or complexity theory or emergence or whatever it is. Fluctuation theorems and non-equilibrium statistical mechanics. I like all those things, and I think other people should like them too. But I get it that not everyone has the same interests I do. So again, I'm interested in a broad ecosystem where everyone is enthusiastic about their own stuff, and we see where it goes. Now, having said that, those are all easy things to say. At some point, the rubber hits the road. You have to actually choose who to hire into your physics department, right? As a member of a physics department that is going to be hiring people, I'm part of this conversation. And I don't know how clear it is from the outside, but the faculty members in the physics departments, as in other departments, take this responsibility super duper seriously. We talk to each other. What are the fields in which we should grow? What are the possibilities of breakthroughs? What are the growing young fields? What are the fields where we have strength and can do better? All of these things are taken very, very seriously by grown-up faculty members. And so they try to do their judgment as best as they can when it comes to hiring new people, et cetera. Having said that, there is a kind of conservatism among academics, right? There's certain subfields that have been successful and high prestige for a long time, and it's very easy to just keep doing those over and over again. It is harder to see the value in a field that is sort of a new upstart field, right? So that's why, I pointed out when the Nobel Prize just came out for these people who were doing experiments in quantum entanglement, these experiments were not super duper high priority when they were originally done, okay? It was like sort of a niche kind of weird thing, and still many people, many physics departments don't have people working in those fields of quantum information, quantum experiments, entanglement, things like that. So there is some effort that needs to be put into convincing a bunch of people who've been doing things a certain way for a certain number of decades that they should look at newer areas that are very exciting. The problem is that old areas that are well established have well understood criteria for success, right? If you're doing experiments in astronomy looking at the cosmic microwave background, we know exactly how to do that. We know what we're looking for. We know what would constitute a wonderful discovery. If you're doing experiments in fluctuation theorems and non-equilibrium statistical mechanics, that's a much smaller area. It has not been going on for as long, and you have to do some sales pitch to your colleagues in the physics department to say, this will be really important someday, right? And that's kind of okay. That's how it's supposed to work. There are some things people get enthusiastic about that turn out to be completely useless. So you have to make that sales pitch. So I would like a little bit more of openness to new ideas and young fields, but I understand why the arrangement is what it is right now. Joachim asks a priority question. As I understand it, each photon from the CMB has been traveling billions of years before reaching us. It must have been deflected by all the gravity of the material and energy it came across during its travels. I am aware of the calibration of the CMB effort by backtracking photons through the universe as we know it, in light of the discoveries of JWST of large, previously unknown structures forming very early in the universe. How can we be certain that the distribution of the temperature fluctuation of the CMB is correct, and that possible features such as Hawking points aren't scrambled by these displacements? Well, this is a very good question, but it's a very quantitative question, okay? The numbers actually matter. You know, the discoveries from JWST of larger than expected galaxies are still tiny, tiny variations from the overall picture, right? They're still quite compatible with the general idea that the fluctuations in density at early times were very small and have grown over time. It's not a major rethinking of the way that we thought about the Big Bang model or the growth of large-scale structure. That's one thing to keep in mind. The other is that there will be deflection of light from the CMB by gravitational lensing and things like that. In fact, I wrote a paper. Here's an amusing Mindscape attached story. I wrote a paper when I was a grad student, or maybe when I was a postdoc, with my grad school colleague, Ted Pine, on second-order gravitational perturbations of the cosmic microwave background, long before anyone had observed these things. So by second order, we mean there's some perturbation to start with, and then you perturb it again. For example, you have some perturbation at the surface of last scattering where you make the CMB, and then you perturb it again by traveling through an inhomogeneous universe. So we presented one way of actually calculating that, maybe not the most computationally efficient way in retrospect, but it's important to be first, not just to be perfect. And so the paper is cited and used in things like that. And an example of that is exactly what you're talking about, the mixing up of the location of different things by gravitational lensing. That's one of the effects that we identified. And the Mindscape connection there is that Ted Pine, after graduate school, he did not pursue an academic career, but rather started a band. And his band, Euphonic, is the band that whose song is the intro and outro songs for Mindscape. So the Mindscape theme music was composed by Ted Pine, who I also collaborated with on that CMB anisotropy paper. But anyway, to answer the question a little bit more directly, the kinds of deflections that you get through photons passing through gravitational lensing from large-scale structure, et cetera, exist, but are typically on very small scales. So cosmologists know this. When you look at CMB fluctuations on very large scales, it's irrelevant. It's just not a big deal. Large scales, that is to say, large angles on the sky. Most of the work that we've done determining cosmological parameters from CMB observations take advantage of these large-scale fluctuations in the CMB. The place where the gravitational lensing will be important is for smaller scale perturbations, and people know that that's important, and they're using that. That is one way to learn about the distribution of density fluctuations throughout the history of the universe. You also, even if the initial perturbations that JWST is looking at are bigger than expected, they're still not as big as the more modern, more recent fluctuations in density with galaxies and clusters and all that stuff. So my impression is that most of the relevant lensing happens at later times, not at super early times. Slippery Snake says, I used to be a moral constructivist, but encountered David Roberts' explanation for why he quit before finishing his PhD in philosophy. The main idea being, it's not moral principles, but moral agents that matter most. Are agents more important than principles? And if so, does moral constructivism matter? So I'm probably not going to give a satisfactory answer to this, but I'll say two things. Number one, I have no idea what it means to be a moral agent unless you have some moral principles. Like, how do we know who the moral agents are? I mean, I presume a moral agent is one that acts morally according to some principles, right? So I just don't get the distinction here. And the other one is, if so, does moral constructivism matter? Again, I don't quite see what the relationship there is. A moral agent is going to act in some way. Is that way objectively figured out by reason or by the universe, or is it constructed in some more subjective human way? So I think that moral constructivism can be completely relevant even if your focus is on moral agents rather than principles. Now, it might be true that there is some way of looking at morality and moral guidelines that is more useful by focusing on moral agents than moral principles. That might be true, but I just don't know. I'm not exactly sure of what David Roberts or anyone else is trying to say about that. But I don't think there's a deep fundamental distinction there. It might be, at best, a practical kind of usefulness distinction. Spencer Hargis says, Darwin and others provided an explanation for how the fruitfulness of living things could have emerged naturally over time without divine intervention. Now that space-time seems to be multiplying as well, it seems natural to ask whether the fruitfulness of space-time and the conservation of its energy could also have been optimized over cosmological time by a process of selection. As a physics fan, I'm curious to know how this concept strikes you. Is it the sort of obvious question which you and your students and colleagues are already discussing over drinks? Well, the idea that laws of physics evolve over time is certainly one that has been discussed by lots of people in lots of different ways. In some very obvious way, the cosmological multiverse idea proposes that different parts of the universe have different laws of physics, and depending on your criteria for reproductive success, maybe that is an example of this. In a more direct way, Lee Smolin, former Mindscape guest, proposed precisely a theory that he calls cosmological natural selection, or cosmic natural selection. His idea was at the center of black holes, you would create a new universe, and for some reason, which is more or less magical, the new universe you create has slightly different laws of physics in it, okay? This idea never really caught on for two reasons, I think. One is that the mechanism by which you made a new universe inside a black hole and the mechanism by which that new universe has slightly different laws of physics was just never specified. Like, there's no known reason why physics should act that way. We just think that what happens in black holes is you make a singularity, not a new universe. That could be wrong, and people think otherwise, but that's the usual way of thinking. So this is just part of setting one's credences in new theories. And the other thing is that if, at least naively, straightforwardly, not thinking very hard, what that mechanism would do would seem to optimize for creating more black holes, right? Using the analogy with natural selection, you want to, natural selection doesn't optimize success, in any sort of vague way. It specifically optimizes reproductive success, sending your genome onto future generations, okay, by having kids and having them survive. So it would seem that the relevant laws of physics would be the laws of physics that let you make new universes, i.e. make lots of black holes. And it seems to me that our universe is nowhere close to optimizing the number of black holes that it could make, right? We have black holes, they exist, but the number of black holes in our universe, as far as we know, is way smaller than the number of stars or planets or whatever. And it doesn't seem that hard to imagine different laws of physics that would make it much easier to make black holes. So if anything, the data seem to be against this particular idea. Having said that, there's other ways that laws of physics could evolve besides Smolin's theory, and I'm actually thinking about that myself these days in the context of quantum mechanics. But it's all very far from connecting with reality yet, so I wouldn't hold out too much hope that this is going to be something established very soon, anytime soon. Dan O'Neill says, do you feel physicalism in your bones? For example, when in conversation with another human being, are you comfortably able to think of them as a purely physical system, or would you have to stop and remind yourself of this fact? Well, on the one hand, yes, I'm comfortably able to think of them as a purely physical system. On the other hand, I don't feel any need to stop and remind myself of that fact, because as a good poetic naturalist, I recognize that there's more than one way to talk about a system like a human being in the universe. Human beings can be physical systems, and they can also be human beings with wants and desires and all that stuff. I think all that is true. I do feel it in my bones. I feel no objection to it at any intuitive level. Rue Phillips says there's a great new documentary on Netflix called A Trip to Infinity, complete with multiple Mindscape guests. There's a really moving part where Alan Lightman talks about how as a young person he was very depressed and sad about being a speck in an indifferent universe doomed to nothingness. But then he found love and his perspective completely changed. It didn't change what was true, but what was true for him personally and gave him meaning in life. For your listeners that struggle with this cosmic perspective of being a speck in a universe that doesn't care, what advice would you give? Any personal, relatable experiences you can share? Well, again, I'm always feel inadequate trying to give advice about these kinds of things because every individual person is different. Every person is going to respond to different kinds of things. I never really felt bad about being a speck in a giant universe. It's true. The universe is very big, doesn't really care about me that much. That never really bothered me. Why should I care about the fact that the universe doesn't care about me very much? My concerns are much smaller scale in terms of my everyday life than the great expanse of space and time throughout the universe. I care about the people I interact with and can affect in some way, whether it's through personal interactions face-to-face or through podcasts or through books or whatever. Students in my classes, that's what I care about, right? Trying to make the actual Earth a better place is more important to me than the fact that most of the cubic centimeters in the universe are empty and don't have life in them at all. Having said that, it's absolutely a good question to ask. How should we shape our lives? What does give them meaning? What does matter? I did a podcast about this. I did a whole podcast on meaning, solo podcast a couple of years ago. So you can check out my ideas there. And I, tentatively suggested that we can think about meaningfulness as arising from fighting against what is easiest or just comes without any effort, right? What are the ways in which by exerting our agency, we can change the world from its course and to make it be something better? And that might be as small as making your children or nieces and nephews happy by giving them a present, or something as large as combating climate change or something like that. There's various ways in which you can make changes in the world in a positive direction. They don't have to be cosmic scale. That's okay. I don't see why that should be the natural comparison. Much more human scale things are usually what matter to people most, like falling in love. That's a perfectly good example. JS says, is complexity observer dependent? We say that a coin flip is simple because we allow ourselves to model it probabilistically, and the probability distribution of a coin flip is simple. But to Laplace's demon, who can model the dynamics exactly and presumably can predict specific outcomes exactly, wouldn't a coin flip in fact be very complex? In general, does the world appear more complex to a more sophisticated observer? So the short answer here is it completely depends on your definition of complexity, which is not something we have a once and for all definition for. Like life or like intelligence, as we talked about earlier, complexity is something that has different aspects that will be relevant under different circumstances. Having said all that, there's absolutely a kind of complexity that is observer dependent, that involves a coarse graining. But you don't even have to think like weird things that are ill-defined like complexity. Just think about entropy, right? Entropy is pretty well defined and we know what it is. And Laplace's demon wouldn't need it because Laplace's demon sees every particle and doing everything. Entropy comes about by coarse graining, by saying that a whole bunch of microstates, for all intents and purposes, form the same macrostate. They're indistinguishable from each other. To Laplace's demon, every microstate is distinguishable from each other, so they don't need to talk about entropy. Laplace's demon doesn't see an arrow of time. They just see different states at different moments. That's all that they see. So to that extent, yes, in exactly the same way, to an observer who only sees coarse-grained features of the universe, then they will think about complexity in a different way than an extremely hypothetical and in fact completely physically implausible observer who sees every single microstate. Gregory Klusnick says, what's your credence on the feasibility of building a high-resolution neutrino telescope that could see beyond the CMB, and what sorts of interesting things would you hope to see there? Well, I think that my credence is pretty low. I think it would be awesome just to detect the cosmic neutrino background, which we've not been able to do. So for those of you who don't know, there's, of course, the cosmic microwave background, the photons from the Big Bang, and we can only use those to see back to the surface of last scattering, the moment in the history of the universe when the universe went from being opaque to being transparent, about 380,000 years after the Big Bang. There is also a neutrino background. We're quite sure that it's there. We can sort of implicitly see the importance of those neutrinos to the cosmic energy budget. So it's got to be there, but they're very hard to detect because neutrinos are just very hard to detect, and these are especially low energy neutrinos. But we can imagine it, what if you could see the neutrinos? And in that case, you'd be able to see beyond the surface of last scattering, right? Because neutrinos were never in an opaque environment. Neutrinos were just freely streaming. So you would see way back to a much earlier time in the history of the universe. But even though that's true as a function of time, so you would see back to the first fraction of a second after the Big Bang, I think that what you would actually see is pretty much the same as you would see in the microwave background, because in terms of actual distance that you're looking further, you're looking billions of light years back to see the surface of last scattering, and then a couple extra 100,000 light years from that to see what the neutrinos came from. And I don't think that physical conditions are going to be that different 100,000 years or 300,000 years, light years away from the surface of last scattering that we actually see today. So it'd be great to see it. I love it. I don't know how to actually technologically do it, but I wouldn't imagine any completely astonishing discoveries coming from it that are not already implicit in our knowledge of cosmology. Simon Carter says, when promoting your new book, how do you decide which podcasts, talk shows to go on? I don't have a system, really. I will confess that I turned down a lot of invitations. Since I started my own podcast, I used to more or less try to go on podcasts, especially if they were, young, struggling, new podcasters, and I would try to go on and help and things like that. But I only have a finite bandwidth for doing podcasty things in my life. I have other things to do. I have to teach and do research and write books and things like that. So now the fact that I'm both creating my own podcast and preparing for it and all that stuff, that is almost all of my podcast bandwidth. There's a couple of exceptions for either people who I know or if I have a new book coming out, but even for the new book, I've had to restrict it to the biggest hits, the ones that would actually do the most good for me promoting the book, right? That's the basic criterion. There's some that I don't want to go on just because I don't like them, and I don't want to get involved in arguments or anything like that. I just want to talk about science. But mostly it's just, what do I get the biggest bang for the buck? Because I just don't have too much time to do other people's podcasts. Brendan says, you and other cosmologists have stated it could be possible that time is infinite in both directions, past and future. However, I've heard some theologians try to discredit this consideration by saying if there's an infinite amount of time in the past, you would never get to today because it would take an infinite amount of time to reach the present. To me, this reasoning sounds a bit flawed, although I'm having a little trouble articulating the underlying issues. Would you be able to help weigh in on why it is not necessarily correct to say that the present would never happen if the past is infinite in time? Yeah, I've heard that argument. It's a really bad argument. It's like saying the number 0 can never be obtained because starting from minus infinity would take infinitely long to count to 0. The point is you don't start from minus infinity. You just start from whatever point you want and go in both directions of time. So the part of the philosophy behind imagining that time is infinite is that time is not something that started. Right? That's those two ideas, time is infinite and time started, are incompatible with each other. So if time is infinite, there was no starting point. That's the way to think about it. And therefore, the idea that you would never reach the present starting from the starting point is just a mistake right from the start. Matt from Sweden says, it seems to me like there have been few major theoretical breakthroughs within physics during the last decades compared to the early 20th century. If so, could this be attributed to the low-hanging fruits have already been picked, or simply that we don't have another 21st century Einstein or Max Planck? So it's definitely not the latter. It is definitely not that we don't have another 21st century Einstein or whatever, both because we do have an enormous number of super smart, talented people right now, and also because other people would have done what Einstein and Planck did if they had not been around. Okay, so it's not like they were just singular geniuses back at the time. It's much closer to the other idea that the low-hanging fruit has already been picked, but let's emphasize it wasn't super duper low-hanging fruit. Things like the theory of relativity or the Big Bang model or quantum mechanics, okay? I think that the way to think about it is sort of a little bit backwards from the way that it is usually put. It is not that the last few decades have been slow. It's that the first half of the 20th century was just absolutely amazing and atypical in the history of science, okay? The idea that you would have multiple scientific revolutions all during a few decade period, which we did with relativity, special and general relativity, quantum mechanics, quantum field theory, Big Bang theory, modern particle physics, all of these things in a really short period of time. You just can't get used to that. Like the history of science has never been like that. We really did get lucky, or the people who lived at that time were lucky to be living in that time that was so exciting in terms of physical discoveries. So the second half of the 20th century was more or less in fundamental physics, where I live, a story of coming to terms with the discoveries that were made in the first half of the 20th century. You know, we already had quantum field theory, but we had to figure out how to use it. We already had the Big Bang theory, but we had to find the microwave background and figure out how to measure the density parameter and things like that. We already have quantum mechanics, but we're still working on getting the foundations right, you know, all of those things. And that's just perfectly natural. That's normal science. That's how things are. It could change right away, right? I mean, at any time, a big new discovery or idea could tip over the apple cart. But I think that the rate of progress that we've had in recent years is just much more normal and ordinary than what we got spoiled with in the first half of the 20th century. Okay, I'm going to group together two questions. George Robinson says, all of the beginning quantum mechanics that I learned is based on linear equations, like the Schrodinger equation. But in many disciplines, the physics becomes nonlinear, like in nonlinear optics. Where or how does nonlinear behavior emerge? And Eric Stromquist says, what do you think of the apparent conflict between quantum linearity and classical chaos? For example, a certain YouTuber said that quantum mechanics does not correctly reproduce the dynamics of classical chaotic systems. My guess is that within any given observer's branch of the wave function, the observable quantum dynamics can be consistent with nonlinear chaos because the states observable within the branch are typically mixed thanks to entanglement with things in other branches of the universal wave function. So I don't think it's exactly that, but I think that, you know, there's something that is on the right track here. I mean, the short answer to both questions is classical mechanics can be highly nonlinear. Quantum mechanics is linear, but classical mechanics also emerges from quantum mechanics. It's a limit. It's a limiting case. So there's nothing inconsistent about that. You can have overall linear dynamics in quantum mechanics, and so there's no chaos in quantum mechanics if what you're doing is following the evolution of the wave function of the universe. Everything is linear, and it's actually pretty simple. But we're not following that, right? We're following the evolution of branches of the wave function, which are little tiny particular slices of the wave function. And there is a limiting case. There's a set of situations, a set of physical circumstances in which you get a classical limit from quantum mechanics. And then things can be perfectly chaotic. I can give you an example. The famous example is the tumbling of the moon Hyperion. Okay, Hyperion is a moon of Saturn, which has a very lumpy, uneven shape, and you can do the math and figure out that the tumbling across the different axes of this moon is chaotic, classically chaotic. Okay, it's not hard to create chaotic systems in classical mechanics, and so if you didn't know about decoherence and things like that, and you did the quantum mechanics of Hyperion, so you said, well, its orientation has a wave function, and that wave function will generally spread with time, the quantum analog of saying that the classical behavior is chaotic is to say that the quantum wave function spreads out by a lot. So this isn't the spread of the center of mass location of the moon, Hyperion. It's the orientation. So you should just see a big fuzzy spherical blob when you look at Hyperion, okay? If all you were doing was following the evolution of its quantum wave function in isolation. But as Wojciech Zurek and others have pointed out, you're not doing that. It is not in isolation. It's in a quantum mechanical universe where things decohere. So the moon Hyperion is constantly being monitored by radiation from the outside world, which becomes entangled with it and essentially decoheres the wave function of the orientation. And therefore, when you look at the moon, it is actually in some orientation. It is not a wave function all spread out all over the place. But nevertheless, if you followed in our observable branch of the wave function, the orientation of that moon, it would follow a chaotic trajectory. Again, there's nothing incompatible about those two things. Jeffrey Segal says, in the podcast with Chiara Mingarelli, she mentions that there is at least one supermassive black hole at the center of every massive galaxy. Does that mean that some smaller galaxies don't have black holes at their centers? And is there a correlation between central black hole size and the size of the galaxy? So interestingly, yes, there is a correlation between central black hole size and the size of the galaxy. And this is a bit mysterious. People don't completely understand the origin and evolution of central black holes. As far as smaller galaxies are concerned, it's unclear. It's unclear to me. I'm not an expert. Maybe some expert can chime in here. But I think that the answer is you wouldn't necessarily know if there was a central black hole at the middle of every small galaxy, because maybe the black holes are there, but they're smaller, so they're harder to find, right? But it certainly is an interesting topic of astrophysical research. And just so no one gets the wrong idea, as Chiara said, as we talked about in the podcast, the black holes at the center of galaxies are really, really small compared to the galaxies themselves. It's not that the black hole somehow governs the evolution of the galaxy. That is not the way it goes. It's the other way around. It's the galaxy that is affecting the evolution of the black hole in some way such that bigger galaxies have bigger black holes in them. That's what the research is. Okay, the last question for this AMA comes from Roman Leventov, who says, is there a sort of physics thinking that is widely useful for solving problems in business and life, not just in natural sciences? If yes, do you think physics thinking is reducible to the knowledge of physics ontology plus logic plus solid epistemology? Or do you think there is still something else to physics thinking? Did you attempt to teach readers physics thinking directly in the biggest ideas? So yeah, I do think that there's a sort of physics thinking, and I do try to teach it in the biggest ideas. I somewhat jokingly talk about the spherical cow philosophy. It's getting late in the AMA. The talking is becoming hard. Anyway, yes, there's a way that physicists think and do their research. And to me, the essence of it, besides just being science, obviously there's scientific thinking, right? But specifically physics thinking, as we've already mentioned earlier on, it comes down to the search for the correct simplifications, right? What are the features of the system that you can ignore, that you can get rid of? And I think that the reason why physics works so well is that it's often pretty clear in physics cases what you can ignore, how you can model a system by some much, much simpler system and still capture some of the essence of its behavior. For other systems where things can be much more complicated, that kind of thinking may or may not be useful. So, when I'm thinking about the physics of democracy, I'm certainly not saying that the right way to think about democracy is all to think of it like a physics system. What I'm saying is that thinking of it like a physics system might give certain kinds of insights under the right circumstances. So think like a physicist by all means. Look for the simplifications, try to find simple toy models that give a lot of the behavior and then add in the complications later. But don't be surprised if that doesn't work. If it works, that's great. If it doesn't work, use some other method. That's a good lesson for life beyond physics thinking. So that's a perfectly good way to end this AMA. Thanks, as always, everyone who listens to the AMA, especially the Patreon supporters who make it possible. Thanks for everyone to listening. Hope that everyone buys the books. That's what I hope. I think that would make everyone's life a little bit better. The holidays are coming, right? You need gifts. Don't just buy one book for yourself. Don't, bogart all the books, all the wisdom. Send gifts to all of your friends. That would be great. And talk to you next month.